Yeah. Starting.
Yeah.
Yeah, that is fantastic.
Through Zoom we teach science semester. I think we already have 49 students in check. So I have a feeling that at that point I should be done. Course. The only real student we have I think that link I sent you on refrigeration cycle, with that, I'm not sure we need anything. Right? We cover numbers and things like that. Although the refrigerant that's 122. We can show that with your class. And your class also can also. Okay.
Michael Gieselman may start with Bruce Wallenberg. And I think we probably should start with one course.
Yeah.
Get some confidence.
Yeah.
Right. And then.
So do you want to hook this up?
Not now. No. We can do that. Yeah. Some break, you know. Right now it's nice to have this arrangement. So what I should do is bring up the So if I want to go to a file on Cusp,
yeah.
I have to click here. We are here, right?
We can minimize this.
Minimize this here. Okay, and then?
The file is on Cusp, right? So we can just put cusp.umn.edu.
So we have to go to the, Cusp. Cool video slides, right?
No, that's video modules.
Yeah. I think I want to just start with video modules. Okay. And the one we are looking for is this thyristors. So that is,
well, the next one.
It's 27, 28. So 28 is space vector, ancillary topics.
Yeah, that we've done.
And 29 we have done.
So 31.
So 20, that's 20, 27, 29 is this.
29 and 30 is
30 here. So, you know, in the smaller screen, it all groups up, right?
Yeah.
Trying to.
Yeah, I'll look into how we can reorder those.
Sure. In this segment, we will introduce converters. Okay. So now this is where I want to go. So, so what I have to do is I'm ready to go here, and this thing seems to work, right? So I go here, zoom, to show my picture.
That's here, I think, right?
Here. No, this is this here.
Or is it here?
Yeah. We minimized it,
Oh,
right?
that's here, actually.
Right
so
here.
You can click on this icon here.
This one?
The next one.
This one here. Okay. Okay. Right. Okay.
And then at, in say about 5 minutes when we begin, then we can start the screen share and then we can.
Sure. Good morning, everybody. We'll begin in 5 minutes. So, and then if I want chat box, there's a chat box here. Just to learn here, Abhijit.
Yeah.
So if I click on chat here,
it'll open up the
chat box here. So now I have access to chat box.
Yeah.
And this here. And if I go to participant management, I can see who's logged on at the moment, right?
And then, so these are all the list of users, your
and
chat
chat
is
box
here.
So if I don't want the whole screen, I could keep it like this, right? Yeah. That's the best. I mean, so what they see is the whole screen probably.
Well, they can choose, right?
They can choose. They can also see the chat box and the participants, right?
They can choose what they want.
Sure.
They can also toggle when you're speaking. They can toggle between video and the slides.
Yeah, very good. I think this is a fantastic. And recording.
Recording is on.
Are you sure?
Yeah.
Okay. This is all we should teach with 17 of 1. Now I'm thinking that why teach it only once a week? You know, we haven't really specified the times. We could make it 3 times a week.
3 times a week?
Yeah, you know, the online course.
Oh, okay.
Right now it was online, it was kind of flipped classroom manner, right? But let's say we don't get to make all the videos and things like that. Then we, you know, first time teaching it, I could keep it.
Purely for.
But certainly, oh, something happened here because you're showing up.
Yeah, I'm going to shut my camera because.
No, that's okay. You can be seen, right?
Actually, because I'm co-host, it enables video by
default. Yeah. Sure. Yeah. So I think thyristor converters are coming back. If you're going to use LCC for HVDC, it is an option if you're talking about high power, long distance, right? There could be a combination of LCC and VSC, right? Right. So
actually, I didn't quite understand how, if you have two LCC on two sides, then they are current controlled, right?
Yeah.
So then how do you have VSC taps in the middle? How would that, how would you control like the voltage and current on the line?
Yeah, you have to have some capacitors, I think, across the VSC, right? So you can see the VSC terminal, the port could be think of as the other end. So when you have LCC, you really have the current.
Basically, the line is like an inductor, right?
Yeah, like an inductor, right? Something to look into. I don't know. Nobody, to my knowledge, at least I have not looked into it. That could be part of this project, research project. So to transition to those video, I just have to click on this. No. To transition to the video, what do I have to do?
No, it was not in meeting. We just
So,
say share and then we switch to
share, this one here.
Yeah. And we can keep the video page ready.
I think it's ready, I think. Or at least I can show it once I get there. To share.
Yeah, another maybe a minute or so and then we can start.
Sure.
8:29 by my clock here.
I'm looking at the cell phone. Should be very accurate. Yeah, 8:30, right? Okay, good morning, everybody. So this is the beginning of the third day for us. And so I'd just like to go over the agenda that this morning. We look at thyristor-based converters. And then we also look at multi-modular converters, MMCs, and dual active bridge, which is very essential in charging of electric vehicles. So that's the agenda for this morning. And then after lunch, Dr. Shisagar will talk about EMI and EMC, and our postdoc, Dr. Siddharth Raju, will tell us about the lab we have, which goes with this course that we have been teaching for many, many years. And now we are upgrading that lab using wide bandgap devices and a digital controller. So that's not quite ready yet, but we hope that it will be ready by the end of this year for power electronics. It is already ready for electric drive. So let's begin. So what I'm going to do is start with this one.
Yep.
Share. Share. This one here. Okay. So we'll start this video on thyristor rectifiers, which is module 30, which is this one here, right?
Mm-hmm.
Very good. So I click on this.
In this segment,
and then
we will introduce thyristor converters. We'll look at the applications, basic principles, and single-phase thyristor converters. Thyristor converters today are being used at mostly at pretty high power levels, and their operation would be on three-phase systems. But in order to understand how they operate, we have to start with the basic principles and first look at their operation in single-phase circuits. So the applications are, most prominent application of thyristor converters is in high voltage DC transmission systems. So let's begin. We have seen these solid-state power devices and their current handling capabilities and their blocking capabilities. The symbols are shown here. These are switches which can be turned on or off by control signals or by the gate circuitry, if you will. But thyristors, they are in a class of their own, where they have, you can call them sort of a semi-controlled switch. They're not a fully controlled switch as such. And they can be made to operate at very high power levels, very high voltages and very high currents. So we are familiar with the diodes. Diodes have just this anode and cathode, but thyristors are a four-layer device as shown here. They have an anode, they have a cathode. In addition, they have a gate, which allows us to be controlled in a way that we will look at shortly here. So let's put a thyristor, the symbol is shown here, in a very primitive circuit. So the input is, let's say, a sinusoidal EC voltage, and at the output is just a resistance. Okay. So if this thyristor were to be a diode, as soon as this voltage becomes input voltage becomes positive, current would begin to flow. Okay. But since we have a thyristor, even though this voltage across this thyristor, this is anode here and this is cathode here, even though the voltage across this has become forward biased, we can prevent it from conducting until the gate pulse comes at this angle alpha over here. So this is the gate pulse, which is this current I sub G flowing into the gate of this. So we just need to supply a pulse of this current, and then this thyristor begins to conduct, and once it begins to conduct, it latches on. Okay, and once again, we think of it for our discussion purposes. It's an ideal in the sense that voltage drop across it is essentially zero. We are assuming that, and so we can neglect that here. So we can see here that at this angle alpha, when the gate pulse comes, this thyristor begins to conduct here, and therefore this VD becomes equal to Vs, as shown here, right? And the current begins to flow, which is this current is just Vd over R, and therefore it has the same waveform as Vd. And then at some point, actually at this point, the voltage goes to zero, current goes to zero, and then this current cannot reverse, just like in a diode circuit, and it becomes zero over here. So as you can see here, we have a waveform shown in this in bold, which is the waveform across this resistor V sub D, and it has an average value which can be computed over one complete cycle here by integrating this voltage V sub D waveform. And you can see here that we have control over its average value by controlling this angle alpha. So this is an extra degree of control that we wouldn't have if this were to be a diode here. So let's extend this. Now the load on the DC side is an inductive load. It also has inductance, not just a resistance here. So once again, we can delay the conduction of this thyristor by this angle alpha at which this gate pulse comes. This is angle alpha. And so the current begins to flow in the circuit once it turns on. This current begins to flow. But because this inductance over here, even when this voltage has gone to zero at this point, the current is still finite. So that current has to have a path to flow, and that keeps this thyristor conducting until this current goes to zero, and then becomes then stays zero until this instant, when once again after this angle alpha, this thyristor is gated on. So the bottom line here is that once the thyristor begins to conduct, the gate loses control, if you will. Okay, and only after the current comes to zero until the circuit in which this thyristor is connected, this gate regains control. Okay, and in this case, what we see is that even after this voltage has gone to zero, the current is still flowing, and this V sub D is equal to Vs, which has become negative. So we also have this negative portion here, and then at this instant, when the current goes to zero, then Vd again becomes zero here, and this current is zero. So once again, we can find this average value of V sub D based on the amount of inductance we have, as well as this angle alpha here. So having seen those basic principles, let's put this let's put these into test in a single phase thyristor conversion. And these thyristor converters consist of 4 thyristors, and they are numbered 1, 2, 3, 4 because for positive half cycle mostly 1 and 2 would conduct. And I shouldn't even say that positive half cycle. For half cycle, I should say 1 and 2 would conduct. For the other half cycle, 3 and 4 would conduct. Okay, and they will conduct in the sequence shown here. So 1 and 2 as a pair, and 3 and 4 as the other pair here. To see how they operate, how this circuit would behave, first of all, let's neglect this inductance here. We'll take care of it later on. And let's assume this I sub D to be some constant current as shown over here. Okay, ID here. So that current is always flowing, and so we have this simplified circuit in which we'll look at the operation. Okay, so just to review, what would be the case if instead of thyristors, we had diodes here, and we redraw that single phase circuit as shown here, where 1 and 3 make up the top group, and 2 and 4 make up the bottom group here. So one of them would conduct from the top group, and the current path will be completed through one of the diodes in the bottom group here. And let's assume that on the DC side, the inductance is very large. So this current ID basically has is the DC. This IDR is DC here. Okay, and so you can see here that when V sub S is positive, the input voltage is positive, diode 1 and 2 would conduct here, and then Vd is equal to Vs. So when 1 and 2 are conducting, V sub D is equal to the incoming voltage. And then as soon as this voltage becomes negative, then 3 and 4 take over. So there's instant change of current from pair 1 and 2 to pair 3 and 4. In that case, V sub D is equal to minus Vs. So that's why the waveform for V sub D would look like this here. Okay, given by this expression over here. All right, and the current waveform at the input here would be positive during this half cycle and negative during this half cycle here, like this here. So that's how a diode rectifier circuit in single phase with these assumptions under these conditions would operate here. So let's see what happens when we replace the diodes by thyristors. Okay, so now we have an extra degree of control, and so these thyristors 1 and 2 are ready to take over when this voltage V sub S has become positive. Okay, so they are ready to take over at this instant of time, which we can call a natural instant of conduction. But since we haven't really supplied the gate pulse to 1 and 2, they cannot conduct. So this current, which we are again assuming to be a DC current like this, since 1 and 2 cannot conduct, 3 and 4 have to keep on conducting. Okay, and when 3 and 4 are conducting, this V sub D is equal to minus Vs. So we have this waveform for V sub D, and then at this instant of time, we apply the gate pulse to thyristors 1 and 2. Immediately, this current shifts from 3 and 4 to 1 and 2. So this current IS jumps from being negative to being positive at this instant of time, and then 1 and 2 take over, and the operation continues. And at this instant of time, when V sub S has become negative, 3 and 4 are ready to conduct, but they cannot because the gate pulse to them is again delayed from the instant of natural conduction by this angle. Let's again label this alpha. And at this point, then the current will shift from 1 and 2 to 3 and 4, and V sub S would be equal to V sub D rather equal to minus V sub S. So it becomes like this here. So V sub D waveform would look like this. Okay. So these things are reiterated in this slide over here. You can see that when 1 and 2 are conducting during this interval from alpha to alpha plus pi over here, Vd is equal to Vs and Is is equal to Id. Okay. And when thyristors 3 and 4 are conducting here, which from this instant alpha plus pi to alpha plus 2 pi up to here, then Vd is equal to minus Vs and Is is equal to minus Id. Okay, so these are the waveforms we get, and once again we can find the average of this voltage V sub D by integrating from alpha to pi plus alpha. We just need to look at 1 half cycle, and so integrate this voltage waveform over this interval divided by pi, because we are just looking at half the time period, and we get this value here. So we can see that this average V sub D is proportional to cosine of this delay angle alpha. Okay, and this is under the condition that we have said that the input side inductance is equal to 0. Okay, and we can also do Fourier analysis on this I sub S waveform. We see that the peak value of this is given by this expression related to how much the DC current is on the DC side. And we can also equate the power. So the power on the DC side is Vd times Id, and on the AC side, it's the product of the RMS value of the input voltage, which we assume to be sinusoidal, RMS value of the fundamental frequency component of the current that is drawn times cosine alpha here. Okay. So we can simulate this circuit in PSpice and get the results as shown here. Here in green, we see the voltage waveform V sub D, and in red we have the input current IS. Okay. So this completes this particular segment dealing with the single phase thyristor rectifiers, and we first started out by saying what applications we are going to be looking at and what the basic principle of operation is.
Okay, so continuing on with thyristor converters, we will go to this module number 31, which is about single phase inverters. So let me click on that. And,
in this segment, we will look at single phase thyristor converters in their inverter mode of operation. Just as a review, we have looked at the single phase converters, assuming that this input side inductance is 0. We can redraw the circuit as shown here, and at the output side, we assume that, let's say, the current I sub D is flowing continuously, and we saw what happens if we were to replace thyristors by diodes, what the waveforms would look like, and what happens if we put thyristors in place of diodes. Then we have an extra degree of control where we can delay the firing pulses for thyristor pairs 1 and 2 and pair 3 and 4, and therefore we have control over the input voltage VD by means of this angle alpha here. So we have seen these waveforms, and so what happens if this alpha, we have thought about alpha in the previous segment as between 0 and 90 degrees. And there we have this V sub D average to be positive. We think of this as a rectifier mode of operation. But if we keep on increasing this delay angle alpha, and we alpha with respect to the instant of natural conduction.
Okay, sorry about that. We'll
these
go back.
devices would begin to conduct if they had gate pulses all the time, or if they were diodes. But in case of thyristors, if we increase that delay angle by beyond,
maybe we need to change it here.
sound, is the sound too low?
Yeah, it was quite low.
Noise is also there.
Noise started coming, yeah.
So can you go to share?
Yeah, I will enable it with the sound, right?
Yeah.
Advanced sharing?
No, just click on share once.
Share computer sound. And then I can share this. And then I can mute the mic. Otherwise it causes an echo.
Well,
So
I don't
mic
think
was there,
it's required, but yeah, you can try it.
See, try it with the mic. So
can you listen in this?
Yeah.
No, here. This white headphone has the audio running.
in this segment, we will look at
No echo?
single-phase thyristor converters in their inverter mode of operation.
You can maybe mute the mic.
Oh, yeah, 1 minute. Actually, I'm not sure why this is. So now right, so we'll start the previous module from the beginning again.
And this module,
Yeah, this module. So share computer sound.
In this segment, we will look at single-phase thyristor converters in their inverter mode of operation. Just as a review, we have looked at these single-phase converters. Assuming that this input side inductance is 0, we can redraw this circuit as shown here, and at the output side we assume that, let's say, a current I sub D is flowing continuously, and we saw what happens if we were to replace thyristors by diodes, what the waveforms would look like, and what happens if we put thyristors in place of diodes. Then we have an extra degree of control where we can delay the firing pulses for thyristor pairs 1 and 2 and pair 3 and 4, and therefore we have control over this input voltage Vd by means of this angle alpha here. So we have seen these waveforms, and so what happens if this alpha, we have thought about alpha in the previous segment as between 0 and 90 degrees. And there we have this V sub D average to be positive, and we think of this as a rectifier mode of operation. But if we keep on increasing this delay angle alpha, and we measure that alpha with respect to the instant of natural conduction, where these devices would begin to conduct if they had gate pulses all the time, or if they were diodes. But but in case of thyristors, if we increase that delay angle by beyond 90 degrees, then what we enter is called an inverter mode of operation. And generally we can increase this up to 150 degrees or so. We don't want to go too close to 180, because then it leads to what is called commutation failure. So we can see that in these circuits, if I may redraw them like this over here, just by a thyristor symbol, AC here and the DC over here, this is Vd and this is ID here. You can see here that in the rectifier mode, both Vd and ID are positive, and therefore power is positive. It's flowing from left to right. But in this inverter mode of operation, where this delay angle alpha has gone beyond 90 degrees, I sub D cannot reverse in these circuits. Okay, so I sub D must stay positive, but this V sub D in inverter mode, I should say positive here, okay, but this V sub D can become negative in the inverter mode of operation, and therefore the power becomes negative. That is, it flows from right to left here, like this here. So that is possible, provided we have source of energy on the DC side. And again, the expression for this average V sub D is given by this, proportional to cosine alpha, assuming again that this L sub S is 0. And we'll take that into account later on. And you can see here that when alpha is beyond 90 degrees, cosine alpha is negative. Okay, so it's showing that the average, this DC voltage becomes negative, and we'll see the waveforms in a second. So this is what's going on here. That this is the instant of natural conduction for thyristors 1 and 2 in the single phase circuit, but we are delaying this gate pulse to 1 and 2 by this angle alpha here. So there is no choice, but thyristors 3 and 4 have to keep on conducting, and therefore V sub D waveform follows minus Vs. So it looks like this, and at this time when thyristors 1 and 2 are gated on, this current Is suddenly goes from negative to positive, and then it's V sub D is equal to Vs, and we get this waveform over here. Okay. So in this inverter mode of operation, where alpha is greater than 90 degrees, we get this waveform. And you can see if you take the average of this V sub D waveform shown in red, it has a negative value. Okay. And that's what we had mentioned earlier, that we are able to get a negative value for V sub D, and the power flow then is from the DC side to the AC side in this inverter mode of operation. And you can also see how the input current waveform, IS, although rectangular, as in the inverter mode, it shifts with alpha. Okay. So that is true in the rectifier mode as well as in this inverter mode, that with respect to the incoming voltage waveform, this IS waveform is shifting depending upon alpha here. So we know that this IS waveform, being a square wave, has harmonics, and these harmonics are inversely proportional to the harmonic order. And in addition to real power that gets transferred, there is a reactive power, and this reactive power is given by this expression proportional to sine of this delay angle alpha. Again, this is being looked at with L sub s equal to 0. So our next task is to see what happens when this inductance L sub s here is finite, as it must be in these thyristor circuits. If there is not enough inductance on the AC side, then we should put some external series inductance. Okay. So in this case, this current commutation, which we saw earlier from one thyristor pair to the next on an instantaneous basis, I sub s was jumping from negative to positive and then negative again. That is not going to happen instantaneously, because this current IS is flowing through this inductance. Okay, and as you know, the current through an inductor cannot change instantaneously. So there is a finite commutation period, and during which we'll see these waveforms here. So let's zero in on the circuit, and let's say that this is, in this Vs waveform, which we have shown, this incoming voltage Vs becomes positive at this instant of time, but we delay the gate pulses to 1 and 2 by this angle alpha over here. Okay, so till that point, of course, 3 and 4 are conducting, so V sub D is following this minus Vs waveform here. But as soon as we gate thyristors 1 and 2, which are ready to conduct, what happens is that all 4 thyristors in this circuit begin to conduct. And the current which was flowing through 3 here is now going to shift to 1, and the current that was flowing through 4 is going to shift to 2 over here. So during this commutation interval, all 4 thyristors are conducting. And as a consequence, this V sub D is equal to 0 here during this interval here. Okay, and when V sub D is 0, and also we virtually have a short here, so all this incoming voltage Vs is being dropped across this inductor here, and that is what's causing the current to shift from a minus value to from a negative value to a positive value. So if you look at this inductor voltage during this commutation interval from alpha to alpha plus u, this voltage V sub s, which is also the inductor voltage here, you integrate that, and we can show here that that's it depends upon the amount of inductance we have and how much the current is. So this expression here gives us the volt seconds that are necessary to make this commutation happen. And that volt seconds, it's the voltage that is coming across the inductor is here, and it's during this interval that these many volt seconds are being applied across this inductor to change this current through it. And that from this expression is equal to this much here. So that's the area, this red area that I have shown, and that is is a reduction in the average voltage that would appear across here. If there was no commutation, then this reduction wouldn't have occurred. But because of this commutation, we can say that the average value of V sub D is reduced by this amount, which is equal to this area A sub U. Area A sub U was this here. This is the area A sub U, but you have to divide it by this pi, because every half cycle that area in volt seconds is lost. Okay, and I shouldn't really be calling it volt seconds, volt radians, because we are plotting these things in terms of omega t here. Okay, so that's the reduction in voltage. So the average output voltage in the presence of this commutation due to this L sub s is the expression that we had seen without the inductance, without any commutation interval, where it was instantaneous, and then we have to divide this term over here. And we can also say that, approximately speaking anyway, this angle phi1 at which the fundamental frequency component of IS, which is IS1, crosses 0, that's the angle phi1, and that is equal to alpha, the delay angle, plus half the commutation interval u, because the length of this interval is u, which we call the commutation interval here. And we can also say that this reactive power here can be given by this expression here. So this brings us to the end of this segment, where we have looked at inverter mode of operation for single phase thyristor converters and how this current commutation occurs. Okay, so now we go to the next one. So let's minimize this thing here and go to the next one, which is three-phase. Okay, so now we look at three-phase, and in this segment, we will look at the operation of three-phase thyristor converters and its application in high voltage DC transmission systems. So very quickly reviewing, directly going to this three-phase thyristor converter circuit, it consists of 6 thyristors, and they are labeled in the sequence in which they conduct. And once again, we will simplify our analysis first by ignoring this inductance L sub s as done here, and by assuming this current ID to be some constant current ID over here, like this. So you can see that these 3 thyristors make up the top group, and we'll call the point at which all these 3 cathodes are connected as P, and these 3 thyristors in the bottom consist of the bottom group, and where all these 3 anodes are connected of these 3 thyristors as N here. So V sub D is equal to Vp N minus V N N here. All right, so let's once again assume or visualize that these thyristors are replaced by diodes. Okay, and remember that L sub s is 0 on the AC side. So as soon as if phase voltage, incoming phase voltage is maximum, the diode connected to that would begin to conduct. So here in phase A, 1 is connected, and then as soon as B becomes maximum, then 3 would conduct, and then when C becomes maximum, 5 would conduct. And on the bottom side, when B is most negative, 6 would conduct. When phase C is most negative, then 2, and when phase A is most negative, 4 would conduct. So you can see that these things are conducting in the sequence 1, 2, 3, 4, 5, 6. So that's how we label them. Okay. So when A is most positive and diode 1 is conducting, we get this waveform for IA. And when phase A is most negative, 4 is conducting. So here 1 is conducting, here 4 is conducting, and we get this particular segment here. But in between, some other thyristors are conducting, so the current is 0 here in phase A. So as far as the current coming in to phase A, or through phase A, is shown here. And we can also see what happens to B and C. These waveforms are just 120 degrees displaced. So at any instant of time, you can see that two diodes are conducting, one from the top group, one from the bottom group. Okay, so and we can also see what this voltage on the DC side would look like. It's this is the top curve here corresponds to voltage at point P. The bottom curve here corresponds to voltage at point N, and the difference of these two waveforms is plotted over here. And during this has 6 pulses, so it's called a 6-pulse waveform. And if you take this 60-degree interval, it consists of line-to-line voltage. Okay, and which two lines? Well, that shifts from one 60-degree segment to another, and we can calculate what the average of this output DC voltage would be. All right, so now let's put these thyristors back in, and you can see that thyristor 1 should have started conducting over here. That would have been its instant of natural conduction if it were a diode. But if you introduce this delay angle alpha in gating that thyristor 1 by this amount with respect to this instant of time, then this thyristor 5 has to keep on conducting, and the output voltage V sub D would follow this waveform to here. And only when we gate thyristor 1 that it will begin to conduct, and in this case instantaneously, assuming L sub s equal to 0, and the voltage at point P would look like this here. So we can follow this for the other thyristors, and each one is delayed by this angle, same angle alpha, with respect to its instant of natural conduction. And we can also apply this to thyristors in the bottom group, and we get a waveform at point N to be looking like this over here. Okay, so the line-to-line voltage then, I'm sorry, not the output DC voltage, which is the difference between this and this, we can obtain by looking at the top curve we get and the bottom curve we get, and what is happening to the current waveforms on the AC side. I sub A would have started to flow over here at this instant of time, where it's delayed by this angle alpha. Okay, so whatever waveform we would have gotten with diodes, it's now displaced by this angle alpha because of thyristors and how we are introducing this delay into their conduction over here. Okay. So once again, in this case, we can obtain the average DC voltage. First, we know that if we were to replace all thyristors by diodes, then just by looking at one 60-degree segment from minus pi over 6 to pi over 6 and dividing it by that 60 degrees, which is pi over 3, we can obtain this expression here. So that's VD0, assuming that there is no delay angle, as would be the case if we had diodes in place of thyristors. But because of this delay angle alpha, there is a reduction in output DC voltage, and that is equal to so many volt radians. Again, these are in radians, so many volt radians are reduced every 60 degrees. So we can obtain that by integrating this waveform from 0 to, if we consider this to be 0 and we consider this to be alpha here, we can integrate this reduction and come up with this expression over here. So the bottom line is that the net average output voltage, VD alpha, would be this term minus this term, which gives us this term over here. Okay, so you can see here that the average DC output voltage can be controlled by means of this angle alpha and cosine alpha here. Okay, so next thing we'll do is we'll look at this effect of having AC side inductance, L sub S, and finite current commutation angle, which in the previous case was assumed to be 0 because L sub S was 0. So here, let's say that initially 5 is conducting here. So let's not worry about in the bottom group, 6 is conducting, this current is flowing back like this, but initially the current was flowing through thyristor 5 like this over here. Okay, and so what's going to happen when we gate this thyristor 1, the current in thyristor 5 would decrease from ID to 0. This current here would go from ID to 0, and this current here would go from 0 to ID here. So the net current here has to remain equal to ID. So as this current decreases, this current is increasing here. And during that interval, the voltage at this point we can show is really the average of the two voltages here. This VPN waveform would be just in the middle of the two waveforms, and if we had 0 inductance, this V sub D waveform would had jumped over here, but because of this inductance here, it's over here, and therefore we are losing this area A sub U in terms of volt radians. So this A sub U can be calculated from alpha to alpha plus U, where the current in thyristor 1 is rising and the current in thyristor 1 is falling to 0. And so integrating that, we find that's equal to this here. So that's the area in volt radians that must be applied across these inductors to make the change in current happen. And this area is being lost every 60 degrees. So we have to divide that by pi over 3, which is 60 degrees, to get this reduction in average voltage, which is given by this expression here. Okay, so I don't know if I said it correctly, but the voltage at point P during this commutation interval is really in between these two waveforms over here, here and here. Okay. So having calculated this area A sub u and dividing it by pi over 3 to get this reduction, we can then obtain the average voltage value in this case where we have finite delay angle and finite commutation interval. So we start with this VD0, and when these two combine, we had calculated them to be this, and then we have extra reduction due to this factor over here. So this gives us the average voltage in the presence of finite delay angle and finite commutation interval. So here we can approximate the current harmonics to be inversely proportional to their harmonic order. We can say, approximately speaking anyway, this angle by which the fundamental frequency component of the input current lags behind the phase voltage to be approximated by this, and therefore the reactive power is given by this expression here. So we can see its application in HVDC systems, where we have AC1 here, and we want to take power from here, generate power here, boost it up by means of transformers, and then rectify from AC to DC. We have this long transmission line, and then at the receiving end, we take this DC and invert it into AC, and then we step it down to connect it to AC2 here. So that's the nature of these high voltage DC transmission systems. And in these systems, the power can flow in either direction here. So we have two types of these HVDC systems. One of them is so-called current link. Okay, and this is what we are looking at here using thyristors. But the other one is using the voltage link, and that is very similar to this voltage link systems that we have talked about. So we will just concentrate on this one here in this segment, and quite often the structure looks like this here, that we have a positive pole with respect to ground. Both sides need not be wouldn't be grounded here, and then we have a negative pole right here, and these poles are generally made up of two thyristor inverters connected in series. One is supplied through a Y-Y transformer and one by a Y-delta transformer. And that introduces, this Y-delta introduces a 30-degree phase shift in the output voltage, and thereby the 6-pulse operation for the voltage here and the current here, from 6 pulse it becomes 12 pulse. And the consequence is that it results in reduction in harmonics, both on the voltage side, in voltage on the voltage side, and in input current on the AC side. So a practical system is shown here by a one-line diagram, this CU HVDC scheme, and you can see that it's pretty much like it, except there are a lot more details that go into it. There's some filtering which is necessary because of the harmonics that are present in the current on the AC side, and we cannot let that go on to the AC system. So this could be on AC1 here, or maybe I should write it here, AC1 and AC2 over here. And power flow here, of course, can be bidirectional. So that is what's shown here in this simplified circuit here, where we have two thyristor converters, one pointing up and one pointing down, and we will define the voltages to be positive at the where the thyristors are pointing up. So you can see VD1 is defined to be positive here, VD2 is defined to be positive over here, and so we know the expressions for VD1 and VD2. They can be controlled by a delay angle in this converter by alpha 1 and this converter by alpha 2. And given these polarities, we can see that ID, on an average basis, this inductor plays no role. This ID is equal to VD1 plus VD2, not minus VD2, but VD1 plus VD2 divided by this resistance R sub D over here. Okay, so we'll operate one of these converters, for example, VD1 in the rectifier mode. So VD1 is positive. We'll operate VD2 in an inverter mode, so that is negative. Okay, so we can see how we can control this ID in this circuit over here. So this brings us to the end of this segment, where we have looked at three-phase thyristor converters and its application in high voltage DC systems. Muted right now?
No, I just unmuted.
So now we go to the next last segment on this, which is converter 33, right? And then we will take a break. In this segment, we will look at high power utility related applications of power electronics. And we have already talked about in other segments that power electronics are essential for renewables-based electric generation. But they also have other applications in power systems we'll take a look at here. So the nature of power systems is changing because of this distributed generation, as shown here. This slide comes from ABB, courtesy of ABB, and you can see that utilities of yesterday and even today, they are somewhat vertically integrated, as shown on the left, but there are a lot of distributed generation that's coming online, as shown on the right here. One prominent example of using renewables is in the form of wind, and it could be using an induction machine with a wound rotor, as shown here, where you see that most of the power from the stator of this induction generator goes into the utility grid, but in the rotor circuit, which has slip rings and brushes, we can inject currents of appropriate frequency and magnitude so that this can provide us with reactive power, as well as it can draw reactive power if need be. But the future is really where we have these PMAC machines or induction machines, I should say, AC machines, either permanent magnet or induction machines, and all the power flows through power electronics based on the structures that we have seen earlier. Another big example of renewables-based electric generation is in terms of photovoltaic systems, where the output is DC. Maybe you're feeding into single phase or three phase, but you have to have power electronics in the middle, and we want to operate these at the maximum power point of these solar arrays. Fuel cells, they produce DC, and so we have to convert that into AC. With renewable sources which are variable in nature, we possibly could benefit from storage, and this could be in terms of a flywheel. So when there's excess power available, we can speed up this flywheel, and power is flowing this way from the utility to the flywheel, and when power is needed in the utility system, we can draw it from here, and the speed comes down and the power flows this way here. So we have seen these power electronics loads, adjustable speed drives, for example, and which could be operated with a simple system like this, but this also could be a switch mode converter here, and the power could flow this way or this way over here. There are other applications like dual feeder. So the power electronics could act like a switch. Normally power may be coming through feeder 1 like this, but if there's a disturbance on this feeder, then this switch opens up and this closes and the power flows like this, and the load hardly feels the interruption of power. Then we have uninterruptible power supplies, where we have a critical load here, and and there's a storage in form of batteries. So even if this utility were to disappear from this storage, we can supply this critical load. There are dynamic voltage restorers, where if you want to maintain the voltage across this load, even though there may be a sag in the voltage coming in, we can inject certain voltage in series to make sure that the voltage across the load remains unaffected. And there are high voltage DC transmission systems. One example of this Pacific Northwest Southwest intertie is shown here, where by means of arrangements like this, power could flow this way or this way here. These DC transmission systems could also utilize voltage link ideas, and this is done in this example of cross-sound cable between New Haven, Connecticut and Shoreham, New York, and this slide comes from ABB. Then there are so-called flexible AC transmission systems, FACTS. So if you look at a power system in terms of this one-line diagram, where you have voltage at one end, this voltage at the other end, and these two are connected by a transmission line, and let's say that's mostly inductive, so just the reactance is shown here, and you can see that the power flow here is downhill on angle. So if this voltage is lagging behind in its phase angle compared to this, then the power would flow from here to here, given by this sine delta. So when delta is positive, because minus is shown explicitly over here, so when delta is positive, power is going to flow, given by this expression, from left to right. Okay, and of course it can reverse if this voltage were to lead this one here. But what it shows is that the power flow that we have depends upon the product of the magnitudes of these two voltages, depends upon inversely on the reactance that we have, and sine of this angle delta, which is the phase angle difference between these two voltages. So it is important to keep the voltages at power system buses to be close to their nominal values, and we can do that by drawing this reactive power, in this case by putting an inductor. So this is the bus over here, and by means of these thyristors here, we can control the amount of reactive power that is drawn from this bus, and if the bus voltage was too high, it can be pulled down, or we can connect this capacitor here. This is just to prevent large inrush currents here. For discussion purposes, we can neglect this, and we can connect this capacitor here to pull the voltage up if the voltage is too low, because in this case the reactive power would be supplied by the capacitor to the bus over here. So this is called thyristor controlled reactor, TCR. This is usually these are called static voltage controllers, SVCs, where the capacitors is either connected or is taken out. But we can control the amount of reactive power in a continuous manner by connecting a so-called StatCom, static compensator. So it's really a voltage link system, if you will, but it's really 1/2 of the voltage link system. We can maintain the voltage across this capacitor from this AC side, but here we can either supply the reactive power or draw the reactive power over here. So it's a very flexible device. Okay, so that's another application of power electronics here. And another application is so-called thyristor controlled series capacitors. This slide comes from Siemens, and basically what we have is a capacitor in parallel with which we have a thyristor controlled reactor, and by resonance between these two, we can control the impedance between these 2 points over here. Okay, and so we can control the amount of power that would flow on this line. Okay. Then a very flexible system is so-called Unified Power Flow Controller, UPFC, where we have this StatCom function being shown over here, and here we are injecting a voltage in series over here. So, because if you look at this power expression here, it was E1, E2, X sine delta. So if you can control this delta, we can also control the power flow here. So this can be operated in several modes. So this is a very flexible scheme, and which is this slide coming from Siemens shows these different modes of operation that we can have. So this brings us to the end of this segment, where we have looked at several utility-related applications at high power of power electronic circuits and converters we have seen.
I unmuted that, so I think we can do it. So let's take a 10-minute break, and let's be back at 9:45. Then we start with MMCs and DAB. Thank you. So
start video.
You get to say that.
Right, and then share, right?
Yeah.
Share. Okay, so I think we are ready to start. It's 9:45 here, and now we'll look at these videos from dual active bridge, a very important topic when it comes to charging of batteries, whether it be for electric vehicles or for residential applications or utility applications, as the case may be, where you have active bridges on both sides. So let's begin, and I'll click on this.
I want to touch upon briefly before we go to the topology, because Hi, my name is Amit Jain. I work for Intel Corporation. Hi, my name is Amit Jain. I work for Intel Corporation. I used to work for Peregrine Power, which is where I did some work on the dual active bridge converter. I apologize that I'm not able to use my webcam because it's creating some disturbance on the audio channel. Okay, so I'm going to talk about the dual active bridge converter, and I've organized the material in 3 lectures. In the first lecture, I'm going to talk about the basic topology and its operating principles. In the second lecture, we'll look at the converter design, how we can optimize the design parameters to get best performance. In the third lecture, we'll look at some variations of the dual active bridge converter, introducing PWM control and some topology variations also. So this is lecture 1 about operating principles. Now the motivations for this type of converter which the dual active bridge converter is are as follows. We want a DC to DC converter which will give us soft switching without adding any auxiliary components. So we want to get soft switching, but we do not want to add any additional L's or C's or switches. We want bidirectional power flow from input to output and the other way, and there should be a need for a transformer, either motivated by a need for galvanic isolation, or if there's a high conversion ratio, so that the transformer helps you utilize the semiconductor devices better. There are 2 points I want to touch upon briefly before we go to the topology, because the topology follows from these 2 basic points. One is the mechanism for soft switching in bridge type converters. So as you may have already seen in load resonant converters, which are basically a bridge converter followed by an LC tank, the way we can get 0 voltage switching for the switches is if the current output of the bridge lags the bridge output. So when you change the polarity of the bridge output, the current polarity remains the same, and the lagging current discharges the parasitic capacitance at the node which changes polarity in voltage, and that is what gives you 0 voltage switching turn on. Once you're able to get 0 voltage switching turn on, then you can add lossless double capacitors directly across the switches, and that will help you get 0 voltage switching turn off also. The second point is about power flow between AC buses. So here we are looking at just an AC system with two buses connected by a predominantly inductive line, and we see the phasor representation for the voltages and the impedance. The power transfer between these 2 buses is given by this expression here, and the things to note here are one, that the phase difference between the two buses is what's predominantly controlling the magnitude of power transfer via the sine phi, and also the polarity of the phase shift determines the direction of power transfer. So with the polarities as indicated here, if phi is greater than 0, then we have power transfer from left to right. If phi is less than 0, then we have power transfer from right to left. One more thing to remember is that in this system, the current is lagging out of the voltage sources. So this is tying back to our discussion of soft switching, and we'll see that in the next slide. So this is again a repeat of the diagram we saw on the last slide. We start with a 2-bus AC system with sinusoidal voltage sources, and we then replace these sinusoidal voltage sources with square waves, high frequency square waves, and then we go ahead and implement the circuit which will generate these square waves. So the DC source followed by an H bridge, and you can use the H bridge to generate high frequency square waves at the bridge output. We do that both at the primary and the secondary side, and the impedance here is replaced by the impedance L here and a transformer. This impedance L will also include any leakage that this transformer has. So this is one way to look at how the topology can be derived, starting from the simple case for the AC system. I'm not sure if it was actually derived like this originally, but it illustrates the two basic operating principles of this converter. The fact that the power transfer is controlled by the phase shift, and that we have lagging current, which gives us 0 voltage switching for the two bridges. So here we look at some of the operating details. To generate the square waves from the primary and secondary bridges, we operate all the switches with 50% duty ratio, and we turn on the diagonal switches simultaneously. So S1 and S4 turn on simultaneously, S2 and S3 turn on simultaneously. So and produce a square wave here. Now the square wave produced at the primary and the secondary are phase shifted by angle phi, and that's easily achieved by simply phase shifting the turn on for S1 and S1S by the same phase angle phi. Now once we know that Vp here is a square wave and Vs here is a square wave, we can now reflect Vs to the primary, and we again have a square wave just scaled by the turns ratio of the transformer. The difference between Vp and Vs prime then is the voltage across this inductor L, and looking at the different values of Vp minus Vs, we can then determine the inductor current IL. So we have 4 possibilities. We could have Vp positive or negative, and we could have Vs positive or negative. So in one case, when the voltage across the inductor is VDC1 plus VDC2, we get a sharp rise in the inductor current in this region, where the inductor current is rising from minus IL0 to IL1. Then we get in this region we get voltage across the inductor to be VDC1 minus VDC2, so the inductor current rises from IL1 to IL0, assuming that VDC2 is a little bit smaller than VDC1. and then we have a similar operation in the other half cycle, just with a negative polarity. So the current ramps down sharply first due to negative VDC1 plus VDC2, and then it ramps down slowly due to negative VDC1 minus VDC2. Okay, so we said that we are going to get soft switching because the bridge output current is lagging the bridge output voltage. Here we are looking at one transition to see how it's actually happening. So we focus on the transition for the turn on of switch S1, which is also the same as the turn on for switch S4. We'll just look at waveforms pertaining to S1. So the transition starts when we turn off S2, the complementary switch of S1. So you can see this blue waveform here. VG is the gate source voltage of S2. We are pulling it low. As soon as we do that, the current which was flowing through S2 now starts flowing in any capacitor which is present at this node. So all of this current IDS S2 transfers to IC, which you see, this is the blue or purple waveform in the lower graph here. And when that happens, this starts charging the node up towards VDC1, and the voltage across this switch S1 starts reducing. So the green curve here in this graph, you can see VDS S1 is slowly reducing because of the current in the inductor. Once this node reaches VDC1 and the voltage across this switch goes to 0, then this inductor current, which is negative out of the bridge, starts flowing in the anti-parallel diode of S1. That's the current you see here. This is ID1. So once VD S1 goes to 0, the current from the capacitance transfers to the diode, and while it's still flowing in the diode, we turn on S1. So you can see this is the red curve here in the graph, the gate source voltage of S1. When we turn on S1, then the current transfers from the diode to the switch S1, and because at the turn on instant the drain source voltage was already 0, we get 0 voltage turn on. The transition for S4, as we said earlier, is identical to S1. The transition for S2 and S3 are also identical to S1 and S4. We just have to look at the other vertex. So instead of looking at this vertex, we will now be looking at this vertex for S2 and S3. The transitions for the secondary side bridge are a little bit different but similar in nature. So for the transition for S1, we have to look at this current vertex, and for the transition for S3, S3S, we have to look at this current vertex here. Okay, so that's as far as the soft switching details go. The current expressions for the inductor current, we can derive these vertices IL1 and IL0. The derivation is quite straightforward. The important thing to realize is that if we are in steady state, then this current is minus IL0, same as this current IL0 at this vertex, only reversed in polarity. So now we know that the current RAM during this time period phi is IL1 plus IL0, and that's happening because of VDC1 plus VDC2 prime across the inductor L, and the current rise across in this time period pi minus phi is IL0 minus IL1. That's happening because of VDC1 minus VDC2 prime. And once we have those equations, we can solve for IL1 and IL0. So here I'm listing the expressions, and I'm trying to hide some of the algebra and just exposing the important aspects. The important thing to note here is that this part I base is essentially a constant depending on the input DC voltage, the value of VDC1, and the impedance of the leakage of the inductance L at the switching frequency, and the remaining part of the expression depends on the phase angle phi and the value of M, where M is the ratio of the of VDC2 prime to VDC1. So VDC2 referred to the primary side divided by VDC1. And what this tells us is essentially when IL0 and IL1 will be positive. We need that for zero voltage switching, and we can now derive conditions for IL1 and IL0 to be positive based on the phase angle phi and the ratio of the input and output voltages. The power transfer in the converter can also be derived now. Once we know the vertices IL0 and IL1, the power transfer is essentially given by the voltage output of one bridge, of the primary side bridge, multiplied by the current output of the bridge averaged over one switching cycle, and that's identical to what you would get in half a switching cycle because of symmetry. So it's easy to see what the power transfer is going to be looking at these voltage and current waveforms. So Vp for this half cycle is just VDC1 and this is the current output of the bridge. So we're going to multiply VDC1 by this current and integrate over this half switching cycle. Because VDC1 is constant, what we essentially need to do is compute the area under the inductor current waveform. So essentially the power transfer would be given by the positive area under the inductor current, which is A1, minus the negative area under the inductor current. So the thing to realize here is that because the lagging current A2 during this time period, which is denoted by this red triangle, power is actually flowing back into the input. So the net power going out of the bridge is A1 minus A2. And once we know these vertices IL1 and IL0, then we can go ahead and compute A1 and A2, and using this formula then we can derive the power transfer. After we simplify the algebra, the expression is a very simple one. Given here, it's parabolic in nature, and we are again hiding some of the algebra in this P base, which is defined as VDC1 square divided by the impedance of the inductance at the switching frequency. The maximum power transfer is achieved at pi over 2, and looking at the expression, it's clear that the polarity of phi controls the direction of power transfer. The power transfer is very similar to what we would get if we did a fundamental component analysis. So what we could do is replace these square waves Vp and Vs prime by their fundamental component at the switching frequency, and the inductance by its impedance at the switching frequency, and then we can derive the power transfer as in the 2-bus AC case. And we come up with this expression. Now this is a sinusoidal variation, but in actual value it's very close to this parabolic variation we get for the converter, and this is illustrated in the figure here. So both for positive and negative phase shift, the exact value of power transfer is very close to what you get when you just do a fundamental component analysis. Now the inductance L is a very important parameter in this converter. We would typically utilize the leakage inductance of the transformer to realize this inductance. However, in a well-designed transformer, the leakage inductance is usually not large enough, and we either have to add an external inductor, or we have to think of another way to incorporate the inductance or increase the leakage inductance of the transformer. So this picture here on the right is one possibility for a high leakage transformer. Here what we are doing is we are intentionally adding a leakage flux path. The center limb of the core is providing a path for flux to leak between the primary and the secondary. So some of the flux from the primary will go and return through the center limb and not link with the secondary, and therefore this center limb will actually give you a series leakage inductance in the transformer. The good thing about using this kind of structure is that now we don't have an additional component, and also we would typically have a lower loss in an integrated structure as compared to discrete realization of transformer followed by an inductance. Just to summarize now, the key features of the dual active bridge are as follows. It comprises of 2 H bridges. It has a very symmetrical structure, and we are able to get bidirectional power flow. There is no inductive filtering in the converter. The power transfer between the 2 DC buses is controlled by phase shift. This is similar to the 2 AC bus case. We have lagging current in the bridges, and therefore we are able to get 0 voltage switching. Because we don't have an inductive filter, we are able to get a single cycle response in the power transfer. So that's the end of lecture 1, and next time we're going to see some of the converter design details, how we can optimize different parameters of the converter to get best performance and minimize the size. Thank you. details. The first design parameter is the transformer turns ratio. Hi, this is the second lecture on the dual active bridge converter. In the first lecture we saw the basics of the converter. Uh, this converter is useful when bidirectional power flow is required, and for example in an automotive system where you might want to connect the 12 volt DC bus with a 42 volt DC bus, or in an electric vehicle between the 12 volt DC bus and a higher voltage DC bus, probably in the hundreds of volts. It's also useful for providing galvanic isolation between DC buses, where you want to minimize the size of the transformer. Also, for example, on a Navy ship, if you want to isolate two different zones on the ship which have DC power systems, then you could use this kind of converter. Another application is interfacing energy storage to the grid. So wherever you have a need to interface energy storage, you need bidirectional power flow, and you typically want isolation. If there is a need for reducing size also, then this converter is ideally suited to that application. So we looked at how the topology can be derived from the simple case of the two-bus AC system. We went through the current waveforms, the soft switching details. We said the current has to be lagging to provide soft switching. We looked at how the power transfer can be derived, and that the power transfer is in the converter is very close to what you would get in the two-bus AC case. And we looked at how you could realize the inductance L as part of the transformer. In this lecture we're going to talk about the converter design details. The first design parameter is the transformer turns ratio. To maximize the zero voltage switching range at nominal conditions, we choose the turns ratio to be equal to the ratio of the voltages on the respective sides. So this follows from the current equations here. So if you choose NP over NS equal to VDC1 or VDC2, then M is equal to 1, and these two equations then just reduce to product of phi with this constant I base to so what that means is, to get zero voltage switching, we want IL0 to be greater than 0 and IL1 to be greater than 0, which translates directly to phi greater than 0. So as long as phi is greater than 0, we'll get zero voltage switching, which means we'll get zero voltage switching down to zero load. So theoretically, with this choice of turns ratio, we'll get zero voltage switching down to zero load. Now, switching frequency is arrived at after a more complex trade-off. It has more factors you need to consider. First of all, based on the power and voltage level, we would determine what kind of switch we're going to use, and also the magnetic material. If the voltage level is below 500 or 600 even, we could use MOSFETs. If it's higher, then we would typically use IGBTs. And then that choice would also place a limitation on the switching frequency. The magnetic material would typically be ferrite if you're operating below approximately 10 kilowatt and you're operating in the tens of kilohertz if you have higher power level, then you would typically use tape wound cores, probably something with nanocrystalline material. And the trade-off here is between the heatsink size, the transformer size and weight, and the efficiency target for a given thermal solution. So the heatsink and the transformer size and weight will depend significantly on how you actually cool your system. The switching frequency will also depend on considerations of switching loss at light load, because with light load we are not going to get zero voltage switching, so high switching frequency will mean higher switching loss, and that would be a significant percentage of the total loss at light loads. The controlled bandwidth is also determined to some extent by the switching frequency. So because we'll be using average dynamics of the system, will typically limit the control bandwidth to approximately 1/3 of the switching frequency. The implementation of the control can also be tied to the switching frequency. So if you have a digital implementation, then typically your control loop sample time will be equal to the switching time period or half the switching time period. And that will the sample time will then add its own sample and hold delays to the control loop. So you have to consider the control loop also when you are deciding switching frequency. The inductance value is the most important design parameter, and we'll talk more in detail about this. We also need to look at magnetizing inductance of the transformer, and like in any other converter, we need to determine the capacitor size on the input and output to make sure the input and output voltage ripple are within the requirements. I just listed some of the design equations. Maximum power transfer, which you can derive from the power transfer equation you saw earlier, the RMS current in the primary and secondary. Again, you can derive these from the waveforms. These are useful to compute the conduction loss in the switches and the transformer windings. You can also compute the transformer magnetizing volt seconds, which will determine the transformer size primarily. And using the inductor current waveform, we can also determine the capacitor ripple current waveform and compute the charge requirements. Now, we said that if we choose the turns ratio of the transformer equal to the nominal voltages on either side of the transformer, then we get soft switching down to zero load. But that's only when the input and output voltages are at their nominal values. If they are not equal to the nominal values, which is typically the case in any power converter, then this variable m is not equal to 1, and we do not get soft switching down to zero load. So for example, if the output voltage is less than the input voltage, then m is less than 1, and then IL0 greater than 0 is guaranteed if phi is greater than 1 minus 1 over m. Because m is less than 1, this quantity is negative. So as long as phi is greater than 0, then we get soft switching. So for for power transfer from left to right, we're going to get soft switching. For HB2, however, the secondary side bridge, M is less than 1 and there is a positive value of phi below which we're going to start getting hard switching. These are quantified here in terms of the power transfer level in this graph. Ignore this red curve for now. So it's the blue curve that we should be concentrating on. So for M less than 1, we get hard switching on the secondary side bridge below some power transfer level. For M greater than 1, we get hard switching on the primary side bridge below some power transfer level. Above this blue curve, we get a soft switching for both the bridges. Now, these conditions just guarantee that the inductor current is greater than 0. It does not actually account for the capacitance present at the switching node. When we account for the total capacitance that is present at the switching node, then we need to make sure that these currents are high enough to discharge the capacitance in the programmed dead time. So what that means is now instead of this being greater than 0, these currents being greater than 0, they have to be greater than some threshold value, and the effect of that is in reality we get soft switching down to not this blue curve but this red curve, which is somewhat above the blue curve. The dead time that we program also determines how effective the soft switching is. So you could make the dead time programmable with the current. This is typically done for the phase modulated full bridge converter, and the same principle can be applied here. So as the inductor currents IL0 and IL1 are getting smaller and smaller, you can start increasing the dead time. As they keep increasing, you can start decreasing the dead time, because you know that for when the current is higher, the capacitance will be discharged faster. The current is smaller, it will take a longer time to discharge the capacitances. I'm not going through the equations relating to the transitions, including the capacitances at the switch node. They are included in the appendix to these slides. I recommend that you go through these. These are required for doing a preliminary design of the converter. Okay, we said that the inductance value is the most important design parameter. Here are some general considerations for determining the inductance value. Lower inductance value will lead to a higher power transfer capability and also a smaller phase shift range that you have to work with in the converter. If you keep increasing the inductance, then you'll finally not be able to transfer enough power through the converter. So there's a maximum value of inductance for given values of input, output, and the maximum power transfer you want to have in the converter. You can come up with a minimum value of the inductance also using this equation. This is not very useful. It may be somewhat useful if you have a resolution on the minimum value of the phase shift. For example, if you have a digital realization and phi has some resolution in terms of number of bits you're using to realize the control. So if your resolution is very low, if your resolution is very coarse, then having a small value of inductance will mean that you cannot control the power transfer to a very fine degree. So you want to limit the minimum value of your inductance in that case. Lower inductance typically will reduce the size of the inductor, and therefore it will be easy to integrate it with a transformer. Lower inductance will also typically lead to a smaller capacitance requirement and lower RMS current in the capacitor and lower RMS current in the transformer and the switches. Higher inductance will enable a wider ZVS range, so we'll be able to achieve ZVS down to a lower power level, and this is particularly important if you're operating away from the nominal input voltage or nominal output voltage. Starting point for optimization is an per unit impedance for the inductance of approximately 0.25 to 0.5 per unit. The base here is defined as or defined with the power base being equal to the rated power and the voltage base being equal to the input DC voltage VDC1, and this inductance then is also referred to the primary side of the transformer. So we saw that there are considerations to choosing the value of L. Reducing L will typically reduce conduction loss in the converter, but increasing L will result in reducing switching loss, particularly at low loads with wide variation in the input and or output voltage. So in a real design, what you do is a numerical trade-off between these aspects: the conduction loss, switching loss, and the size of the inductor, transformer, and capacitance, and come up with value of L that minimizes the total loss and the total size. These are the typical curves that you get when you're doing the optimization. These are for a 10 kilowatt design where both the input and output voltages are 700 volt DC. So in this curve you can see that by increasing L we are able to achieve ZVS to lower and lower power transfers. In this curve you can see that increasing the value of L is resulting in increased RMS current for the FET and also increased average current for the FET. Here you can see the capacitance requirement, and the RMS current in the capacitance is also going up with the inductance value. By the way, just as a point of reference, for this design I ended up choosing L of 100 microhenry as a compromise between the ZVS range, the conduction loss, and the size of the different components. So typically the leakage inductance is sufficient to give us soft switching at high load, but not able to provide soft switching at light load. To increase the ZVS range to lower power levels, it is better to utilize the magnetizing inductance of the transformer. This does not translate to a higher RMS current, significantly higher RMS current, as you would have if you were trying to achieve ZVS just with the leakage inductance. And it acts in complement to the leakage inductance. So what happens is at low loads the phase shift is small and the magnetizing current is also small. As you increase the phase shift for high load, the magnetizing current value goes down. So at high load, magnetizing current is lower and you're relying more on the leakage inductance. At light load, the leakage inductance is not able to help you, but you have higher magnetizing current, so you get the benefits of both magnetizing current and leakage inductance. There is a downside to including the magnetizing inductance. It has a penalty in the maximum power transfer capability of the converter. You can derive this if you rewrite the equations incorporating the magnetizing inductance, rewrite the current equations with the magnetizing inductance also. This factor K2 is given by this expression here, and in this expression this variable K is the ratio of the magnetizing inductance to the leakage inductance. This is not a real problem from a design point of view, because the rated power is typically less than the maximum power transfer capability you have in the converter, and also typically you would have factor of 10 for this K. So if K is 10, then you can see that K2 is just 1 over 1.025, so you're not compromising the capability by a big amount. A factor of 10 between the magnetizing and leakage inductance is a good starting point for design, and again the best thing to do is optimize the design numerically, either by simulating the circuit or by computing the different loss components. Now for the transformer design, what we need to start are the RMS currents in the windings, the worst case flux in each part of the magnetic structure, and this will vary with the load. So at high loads you'll have high flux in the leakage path. At zero load you'll have maximum flux for the magnetizing part of the core. Then we can choose the core areas, starting with some assumption for the operating flux density. Typically you would use something in the range of 0.15 to 0.25 Tesla for 3F3 type ferrite, and something like 0.25 or up to maybe 0.4 Tesla for nanocrystalline tape-on cores. Then you go through a design iteration for the transformer, compute the loss in the windings and the core, and see if the loss is meeting your target efficiency and thermal constraints, whether or not you're able to keep the core temperature down to the operating limit of the magnetic material. The ripple current in the capacitor can be computed from the input and output inductor current waveforms or the bridge output current waveforms. A starting point can be when you don't have any magnetizing inductance, and you can use that to come up with capacitance required to meet the ripple specification. Finally, you should confirm your efficiency in ripple by simulating the entire circuit with known values of the switch resistance, switch capacitance, transformer parameters as designed, and some estimate for the transformer intra-winding capacitances also. Now we just looked at what is essentially the power component design for the converter. The other aspect of the converter design is the control design. So for example, we might have a situation where VDC1 is a voltage source and VDC2 is actually a resistive load, and we need to regulate the voltage on this side on VDC2. So to do that, we know that our phase shift phi is the control variable, and that's what we apply to this converter. Now we need a dynamic model for the converter from the phase shift phi to the output voltage, and based on that model we can then go ahead and design a suitable compensator for the system. So the dynamic model for this particular example is straightforward, and here we'll be concerned with dynamics averaged over one switching time period. That's what this bar over the variable indicates. So the capacitor voltage dynamics are then given by this equation. It's quite straightforward, following from the circuit here. The important thing is the H bridge current output IHB2, and this is computed directly from the power transfer. So this is just the power transfer divided by the output voltage. And we have the same parabolic relation now between phi and IHB2, the output current of the converter. So if you're doing a linear design, we can go ahead and linearize this at an operating condition. So at an operating uppercase phi, this is the gain of the converter, VDC1 or XL times 1 minus 2 uppercase phi divided by pi. And the thing to note here is that this is static gain, so we don't have any dynamics in the converter if we assume that the converter is responding in one switching cycle. This is a first order model, and more complicated models are available in published literature. I've included one reference which talks about a more accurate dynamic model for the converter. So now going back to our control loop, we know this current gain, which is a static gain from phi to IHB2, and this is what's feeding to the load. This is just a simple first order RC system which gives you the output voltage, compare with the reference, and then you design a suitable compensator to get the dynamic response you want and stabilize the system. In conclusion, this is an example of a dual active bridge prototype. It's a 25 kilowatt design. Input and output voltages are 700 volts with a plus minus 20% variation expected. The switching frequency is 25 kilohertz. There are two identical H bridges, one over here, one over here. The gate drive and power supplies for the bridges are on top of the board. The switching devices, which are silicon carbide MOSFET modules, are under the board, mounted on the heatsink. The capacitances on either side of the bridge are these film capacitors on top of the board. This is the transformer. It's made with nanocrystalline core. It has a high leakage, also realized inside the transformer via a separate path for the flux, for the leakage flux. This is the control board for the system. These are some operating waveforms, primary and secondary voltages, and in the lower part the primary and secondary currents. Primary and secondary currents are a little bit different because of the magnetizing current. Here are the measured efficiency numbers. The target efficiency for this converter was 98.5. We were able to get close to that, probably 98.4 at the 10 kilowatt level with silicon carbide, which was significantly better than the silicon IGBT version of this converter. We got a reduction of losses by a factor of approximately 3, and a simultaneous reduction in the size and weight of the converter also by a factor of 3 by going from silicon IGBTs to silicon carbide MOSFETs. That's just an aside to our main discussion for the dual active bridge. So that concludes the lecture on the design of the dual active bridge converter. In the next lecture we're going to look at some of the variations of the dual active bridge converter, PWM control, and some small topology variations. Thank you. Hi, this is the third lecture on the dual active bridge converter. We looked at operating principles and converter design in the first two lectures. Today we're going to talk about PWM control and some topology variations. So the dual active bridge converter has some limitations also. If the input and or the output voltage vary significantly, then the ZVS load range is limited, so we don't get ZVS at low loads, and the load range for which we get hard switching keeps on increasing. Also, the RMS currents in the transformer and the switches, they are also very high at low loads. The transformer core loss also remains high at low loads. We are not doing anything to reduce the transformer core loss. So these factors can be addressed by introducing PWM control, which is what we're going to talk about next. And the other topic that we're going to talk about is the multiport DAB after PWM control. So this is the same circuit of the dual active bridge. Now what we're going to do is utilize one more flexibility in the switching of the switching sequence of the switches. And what we're going to do is, instead of getting square waves for the primary and secondary voltages, we can introduce instead of a square wave, a quasi-square wave on one of the bridges. So either VP or VS can be a quasi-square wave. And from implementation point of view, it's straightforward. What you do is you introduce another phase shift between S1 and S3, and that's what gives you this square wave, this quasi-square wave. So what have we done really? What we are trying to do is, when we did not have this additional phase shift alpha p, then these two edges were aligned, and these two current vertices was similar. So what we are doing by introducing this phase shift is increasing the value of the current at the point where S4 switches, and what that does is in turn it increases the value of the current at which S1S and S4S switch. This is going back to our reasoning for achieving zero voltage switching. We want this current vertex to be greater than 0 to achieve zero voltage switching for the secondary side bridge. And to help with that, what we are doing is separating the transitions for S1 and S4. And we have this converse case when we separate the transitions for S1S and S4S in the picture on the right side. So for m less than 1, when we were starting to lose zero voltage switching for the secondary side bridge, then this extra phase shift between S1 and S4 is actually going to bring some of that zero voltage switching capability back for the secondary side bridge. And for m greater than 1, by introducing a phase shift between S1S and S4S, we are actually regaining some zero voltage switching capability for the primary side bridge. We can go through the algebra, derive the current vertices, and then compute the power going out of each bridge, out of one of the bridges over 1/2 switching time period, and come up with this value of power transfer, these expressions. So here the expressions have been arranged to again to expose some important features. So if you see this part of the expression is the same as what we had earlier. So so what we are essentially doing is changing the power transfer by this quantity, negative alpha squared divided by 4 pi. Essentially we are reducing the power transfer capability of the converter to some extent. And also there's a subtlety in the power transfer. Now you get different modes of operation, so depending on the two phase shift values, now the phase shift between the primary and secondary bridge, and the phase shift that you are introducing between the two legs of the same bridge. So depending on the relative values, you get either this expression, the first one, or the second expression. So this one happens at lower power. The second expression, phi f times 1 minus alpha by pi. Phi f here is now defined as the phase shift between the fundamental components of the voltages on either side of the transformer. So fundamental component of this quasi-square wave and the fundamental component of this square wave, phase shift between those is what this phi f represents. Now just from a control point of view, we are still looking at phi f, the fundamental component phase shift, as a control variable, and this additional phase shift is just acting like a disturbance, or something that's modifying that equation, and we can actually compensate for that in our control just by using a feed forward. We can approximate the system again by the fundamental component of the square waves and the impedance at the switching frequency, and derive the power transfer, which is very similar to what you get with this with these exact expressions. Now we said that we are gaining some 0 voltage switching range. How exactly would we choose the phase shift that we introduced to get the extra ZVS range? So now we have, instead of 2 current vertices, we have 3 current vertices. So if we go back to this slide, so we have 3 current vertices, and we have 3 different conditions for ZVS of S1 and S2, one condition for ZVS of S4 and S3, and one ZVS condition for all of the secondary side bridges, in this case for m less than 1. Okay, so if we rewrite the conditions in terms of this extra phase shift that we introduced, alpha p, then the expressions come out to be like this. The important thing to note here is that S1 and S2 always have ZVS, and there is a trade-off between getting ZVS for the lagging leg of HB1 and increasing the ZVS range for the secondary side bridges. So increasing this phase shift alpha p gives us gives us a higher range for ZVS of S1S through S4S, but when we start increasing this alpha p, we start losing the ZVS capability in the lagging leg of HB1. One compromise here we can make is to equate alpha p equal to this quantity here, and if we do that, then both HB1 and HB2 have 0 voltage switching as long as this quantity phi is greater than 0. And if we now look at what this implies, alpha p equal to 1 minus m times p, this is nothing but equating the volt seconds across the 2 sides of the transformer. So for m less than 1, VDC1 is higher than VDC2 prime. And what we are doing is introducing a duty cycle control for VP, so that the average voltage applied across the transformer on the primary side is now equal to the average voltage that we are applying across the transformer on the secondary side. So the duty cycle that we are introducing for VP times VDC1 is equal to VDC2 prime, that is VDC2 reflected to the primary side. So that's what gives us gives us soft switching for extended soft switching for both HB1 and HB2, all of the switches, and we can derive similar conditions for the case when m is greater than 1. So the output voltage reflected to the primary side is greater than the input voltage. When we use these conditions for the introduced phase shift, and we now plot the ZVS boundary, this is what we see. Without PWM we had the green boundary, with PWM we have the blue boundary. So you can see that when m is close to 1, that we are not really gaining much, but as we go away from 1, if the input and or output voltage is varying significantly, then we start gaining quite a bit in the ZVS range. The increased ZVS range is not the only benefit we get by introducing PWM. So how do we choose the PWM duty ratio in order to minimize RMS currents? We can go back to our two-bus system where the voltages on the AC bus are fundamental components of the square waves we're applying on the two sides of the transformer. So we have these magnitudes and phase angles for the voltages. Now the magnitude for the primary side voltage is being modulated by this cosine of alpha p divided by 2 because we are now introducing duty cycle control for the primary side bridge. You can look at this problem similar to the case of the two-bus system where you're trying to minimize RMS current in the line for a given power transfer level. So we can write down the equation for the fundamental component of the current, and then minimize the RMS value of this for a given power transfer level. So power transfer level is given by the second equation. Keeping this constant, we can minimize I1 RMS and find out what value of alpha p gives us the minimum value of I1 RMS. So after you go through that exercise, you will come up with this value of alpha p. And this is not simply equating the reactive part of the current to 0. That's just one thing to keep in mind. An illustration of this minimization of the RMS current is shown for a specific design in these two plots here. So we have different ways we can choose the value of alpha p, and here I've plotted 4 different ways that you might choose alpha p and see its effect on the RMS current. And this is being plotted for the no load condition. So at no load, what is the RMS current in the transformer for different choices of duty cycle? If we go with the scheme in which we are equating the voltseconds across the transformer, so that's this green curve here for alpha p, then we come up with the green curve here for the RMS current value. If we choose alpha p according to this equation here, then we are getting this red curve. If we include not just the first harmonic but also include the third harmonic and minimize the RMS current including the third harmonic, realizing that we have power transfer again constant given by this equation, then we have this black curve. And if we do a numerical minimization for the RMS current, then we have the blue curve. So you can see that there are different ways we could choose alpha p, and if you just go with the voltsecond equalization across the transformer, then we may not get the absolute minimum value for IRMS, but it does reduce the RMS current quite a bit compared to the case without any PWM control. The PWM control also helps in reducing the transformer size. So the transformer size primarily depends on this product here of the maximum volt second product and the RMS current in the transformer. Without PWM, then we have maximum volt second equal to this expression, and with PWM control we are actually able to eliminate this factor of 1 plus M max over 2. So the factor due to variation in the input or output voltage is actually eliminated from the transformer size calculation. Just as an illustration, if we had a variation of 0.5:2 in M, then the ratio of these two expressions would be 1.33, and you would end up reducing the core area requirement by 33%. So transformer size would reduce by 1/3 just by introducing PWM control. Now we talked about doing PWM for one bridge so far. We could do duty cycle control for both the bridges, and instead of having square waves at the transformer primary and secondary, we could have quasi square waves at the primary and the secondary of the transformer. Now this leads to different modes of operation in this converter. There are in all 5 different possibilities depending on the relative values of the phase angle and the duty cycles that you introduce for the two voltages on either side of the transformer. It turns out that of all these 5 modes, only mode 3 and mode 4 are actually useful. Mode 4 is useful when we have M less than 1. So if the primary referred VDC2 value is less than VDC1, then mode 4 is useful only at low powers. Mode 3 is useful when when M is greater than 1, and again it's useful only when when the power transfer level is quite low. We can analyze these waveforms, derive the current equations, and then use those current values to derive the power transfer, and we can come up with these expressions for the exact power transfer to the converter. We can also approximate this again by the fundamental component, and if we do a comparison, it's pretty close, with some exceptions, particularly for mode 1B. I'd rather skip that detail, but you can look that up in one of the references which talks in detail about PWM control. So I said that mode 4 operation is useful at low power. If we look at the waveforms in detail, the current waveforms in detail, we'll find operation to have this kind of current waveform. And the important thing to note here is that we actually have two zero crossings for the inductor current in each half cycle. So between this point and this point, the inductor current goes from negative to positive here, and then goes from positive to negative again here, and then once again goes negative to positive at this part. So we're getting two zero crossings going from negative to positive, and this is required to obtain zero voltage switching for all the switches. So because m is less than 1, we are looking at zero voltage switching for the secondary side bridge, which is what gets compromised first. Now the turn on instance for all the switches are indicated at the bottom here. So for S1 to have zero voltage switching, we want this current vertex to be less than 0, or ID here to be greater than 0. For S1S to have zero voltage switching, we want this current vertex to be greater than 0, so IB greater than 0. For S4S, again we want this current vertex IC to be greater than 0. For S4 we want this current vertex to be less than 0, that is IA greater than 0. Now we can enforce those conditions just on these current expressions and get zero voltage switching. However, we also have to look at the RMS currents in the transformer, and we want to minimize that so that the loss due to the RMS currents is minimized. So so the thing that we note from these current waveforms are as follows. In this middle graph, there are portions of the current waveform which have a light gray area under it. This is the portion where the primary side bridge is actually freewheeling. So so there is zero voltage across the primary of the transformer between this point and this point. So there is no power being transferred from the primary bridge to the transformer in this time period. So all of this current is actually giving us just loss. So we want to minimize IB and IC, but to get zero voltage switching, we still want IB and IC to be greater than 0. Also, we want to make sure that IA is as close to 0 as possible, because we don't want loss in this part of the current waveform. The area which is shaded with dark gray, that is the part in which some power is being transferred first from the transformer back to the bridge, and then being transferred from the bridge to the transformer. So this entire area which is shaded in dark gray, this is resulting in zero power transfer. What is actually giving us positive power transfer is this unshaded area, which is between these two time instants. So to keep the RMS currents low, we want to bring IB, IC down towards 0, IA up again also towards 0. But to get zero voltage switching, we want IA, IB, IC to be all greater than 0. So that gives us the limiting condition on achieving zero voltage switching and minimizing the RMS currents. So if we just equate IB, IC and IA to 0, we come up with these expressions for alpha P and alpha S, the freewheeling intervals for the primary and the secondary side bridges. And this choice now gives us zero voltage switching down to 0 load. It minimizes the RMS currents and also, now that we are reducing the volt second across the transformer, and as we go to zero load, then phi f goes down to zero load, so alpha p and alpha s both go towards pi, so the volt second across the transformer also go down to zero, so the core loss in the transformer also goes towards zero as we keep going down in load. So this choice of the freewheeling intervals, it gives us all the three benefits: zero voltage switching down to zero load, minimized RMS currents, and also reduced core loss at low loads. We said earlier that the dual PWM is useful only at very light load conditions. So what happens is that we can start with dual PWM at light load conditions, then transition to the single PWM that we talked about earlier as the load increases. The transition point occurs at this value of phi f that's indicated here. And we can come up with a composite scheme which will have a seamless variation in alpha p and alpha s, starting from phi equal to 0 all the way up to phi equal to pi by 2. This is the kind of power transfer you get with the composite scheme. It's the blue curve indicated here. So we started with the black curve without any PWM control. We introduced single H-bridge PWM control, which gives us a red curve. Now we introduced dual PWM control and a scheme to transition from dual PWM control to single PWM control, and eventually to no PWM at the maximum phase shift, maximum value of phi f. So at phi f equal to 90, we don't have any PWM control at all. So that helps us regain all the power transfer capability of the converter also. So if you remember, we said that with single PWM control we were actually losing some maximum power transfer capability. So the difference between this point here and this point here on the red curve. The right plot compares the RMS currents in the converter as the power transfer is increased from 0, and you can see that for the composite scheme we are able to get theoretically zero current at zero load, and it is increasing slowly, and then it merges with the black curve at high power levels. Here are some experimentally measured data. So the left set of plots is for the converter operating with 600 volts on the input, 300 volts on the output, and you can see that with the composite scheme we are able to minimize the RMS currents, and we are able to get a significant boost in efficiency, somewhere from in the 25% region to about 78% region at really low loads. The gain is actually lower when VDC2 is higher, so we are getting closer to m equal to 1. So like we discussed earlier, PWM helps only if you have wide variation in the output voltage or input voltage, and that's illustrated here, but we still get a significant benefit in terms of RMS current reduction and efficiency boost at low load. So that concludes the discussion on PWM control. The dual active bridge converter can be extended to multiple number of ports, so it could be viewed like a power system where you have multiple voltage sources which are separated by inductive lines. So in the two bridge case, we just had two voltage sources separated by one inductance. If we have a three-port transformer, then we can think of three voltage sources, each realized by an individual H bridge, and then these are connected to each other by the leakage inductance of the three-port transformer. Now, the power flow in this system can be analyzed using just fundamental component analysis, and the challenge here is that we want to minimize circulating power flow. So if we want to transfer power from V1 to V2, then we don't want power to flow from first V1 to V3 and then V3 to V2. We'd rather have power flow directly flow from V1 to V2. So this is like a power system problem where we are trying to minimize circulating power in an interconnected power system, and we again have flexibilities over the phase angle of these voltages and also the magnitude of these voltages, so we can introduce duty cycle control to control the fundamental component amplitude of each of the voltage sources. The dual active bridge converter was introduced with full bridges on either side of the transformer, but it is possible to have a similar operation with a half bridge also. So that you can use, instead of a full bridge to produce the square wave, you can use a half bridge to produce the square wave, similar to load resonant converters. So here we are essentially replacing switches and adding capacitors, and we are losing some flexibility also. So now with the half bridge we can only impress a square wave at this winding. We cannot get a quasi square wave, so we'll lose PWM control flexibility on the side that we replace with a half bridge, but we'll save on the number of active devices. And that is the end of this lecture. So we looked at PWM control in quite some detail, and I briefly indicated different topology variations for the dual active bridge converter. There is a list of references I provided. Some of them talk about the initial development of the converter. Some have details on the on the converter design, particularly this reference. This is a very good reference for converter design. There are some empirical comparisons done for this converter compared with other possibilities for bidirectional converters, then this reference is a good reference for small signal modeling of the converter. So I encourage you to go and look at these references and also look at some recent papers on the dual active bridge converter. This converter has become very popular recently because of its simple structure and a simple mechanism to effect bidirectional power transfer um, between not just two DC buses, but even for multiple DC buses. So, so I think it's a very uh, good topology. It relies on some very basic fundamental principles, and it provides a lot of benefits for for converters which require bidirectional power transfer. And that is the end of this lecture. Thank you.
Okay. Hello, everybody. So let's take a 5-minute break and be back at 11:25, and then we'll watch the last segment, which is on MMCs. It's about 50 minutes long, and then let's take a lunch hour break and be back at 1 o'clock, and then Dr. Sagar and Dr. Raju, they will have 2.5 hours to 3 hours of material dealing with our labs that we have, and EMI and EMC. So we may get done about 3:30 or 4 or something like that. And, so that's the end of this course, and thank you very much for attending it. And from here on, I think Dr. Sagar will take over. So, let's be back at 11:25. Thank you. So I should stop it. And I should close it here. But I want to turn it off completely, Mhm. Right here. Be muted.
Okay, so welcome back, everyone. I hope you can all hear me. We will start with the final module of this morning session, and that is on modular multi-level converters.
When you take this.
All know Professor Mohan isn't here today, so I'll be taking the class in his place, and hopefully we'll survive this. So, Professor Mohan gave you a brief introduction regarding the MMCs, and we know they are quite useful in high voltage applications because then we can have a lot of these modules connected in series to meet the voltage stress. So as compared to a conventional VSC based topology where you have a two-level inverter, in MMC we replace these single switches with a number of modules. So doing so, we get away with large number of switches connected in series because we do not have switches rated for 200 kV. So instead of connecting many of these switches in series, we have many modules, and then we get the benefits of improved harmonic performance at the output because we have a multi-level waveform. So we reduce the filter requirements, and we also reduce the snubber circuits required for connecting the switches in series. So Professor Mohan went through all this, and since we have a lot many slides to cover, I'll skip these. So this is the basic topology where instead of connecting switches in series, we have modules connected in series. And these synthesize a near sinusoidal voltage waveform here, which is made up of different voltage steps, and that depends upon the number of modules that we connect. And the basic structure, internal structure of one of a submodule is this, where we have just two switches and a floating capacitor. So we saw the switching states of this, where this is not used in actual modulation. So this is not used when the converter is operating in steady state, because this state means both S1 and S2 are off. So during that, it's just the antiparallel diode which conducts, in this case this, and in this case this. So this exists when we want to pre-charge all the capacitors before the system actually turns on or during faults. So in normal operation, we basically use these two stages, where we either insert the capacitor or we bypass the capacitor. So depending upon number of modules that are inserted into the system, we can synthesize different voltage steps in the output voltage. And we'll see that today in the modulation section. So these are the benefits between the MMC and the two-level. Okay, coming to the modulation techniques, which is the topic of discussion today. We have quite a number of methods to modulate the MMC. Program methods are quite difficult because we need to know the exact time duration for which the modules are going to be turned on. So this is very rarely used. Carrier-based modulations are easy to implement because you have a sinusoidal reference which you compare with a number of carriers to synthesize the output voltage. So phase disposition is basically phase level shifted carriers, and we'll come to that in detail, where we have many of these carriers which are stacked one on top of the other. Alternate phase opposition disposition is similar to phase disposition, where you might have one ramping up and one ramping down. Phase opposition dispersion, you have the alternate carriers with a slope increasing and decreasing. But what we're going to talk about today is phase shifted carriers, where you phase shift the carriers with an angle such that when the reference is compared with this, we get the pulses for operating the MMC's different modules. And then we have space vector modulation, and we saw that in the basic two-level inverter and the matrix converter. So doing for a matrix converter itself was very difficult because it generates just a two-level output voltage. So getting a space vector diagram for a multi-level voltage generating system becomes much larger. So this again is very difficult to implement, because the hexagon formed with the number of vectors keeps becoming bigger and bigger as we go to increase the number of levels. So we're going to focus today on the phase shifted oh, I think I'm blocking. Okay, so the system we saw before was a three-phase system. So that has been simplified to a single-phase system, where the return of the AC grid is connected to the midpoint of the DC bus. And this is the AC voltage which is synthesized, or we should call it M and O. So as we talked about, this entire thing is called a leg, and this thing is called an arm of the MMC, and we call this as the upper arm, and similarly this is called the lower arm of the MMC. Now you see we have some inductances here, and these are called arm inductors. They're basically to smoothen out the currents in the arms, because we'll see that we need the arm current direction for voltage balancing, and also they are to limit the short circuit currents during faults. So we have some smoothing inductors here in the arm, which we generally don't have in two-level inverters. And as we talked about, the switching states are going to be just two. Either the capacitor is inserted or it is bypassed. So as we see, the definition of the switching is like this: in the upper arm and the lower arm, these two switches are going to be complementary, as Professor talked about, because we don't want the capacitor voltage to be short circuited if we have both the switches turned on. So these two switches have complementary gate signals with a dead time for protection, and we define for the upper arm this to be S complement and S, and for the lower it is S and S complement, and we'll come to that in the next slides. So it's just follows the easy thing as we did in the previous slides. So when SI is 0, where we define SI to be this for the ith module, when SI is 0, the voltage, let's forget this and call this VC. So when SI is 0, we get VC. And when SI is 1, we get 0. Right? Because the module is bypassed. Similarly, for the lower leg, it's just reverse. And when SI is 0, we get the voltage 0, where this we can call as VI. Similarly, this we can call as VI. Right? So depending whether the module is inserted or bypassed, we get a voltage generated at the output of the module. And we have many such modules connected in series. So depending upon the number of modules which are inserted, we know what the voltage is going to be synthesized at the output of the system, which is the stepped AC voltage. So does this make sense? Okay, now, so this is the same thing, and VI is basically VC times 1 minus S, where S is the switching pulse. So depending upon the number of modules, the voltage is going to be VC or 0. Now, how does this come? We'll come to that. So VU, let's define this as VU. This is the voltage of the upper arm. Okay, so the sum of the voltages synthesized by all the modules in the upper arm is called VU, which is for the upper arm voltage. Similarly, the voltage, net voltage that is generated by all of these modules in the lower arm is called VL. Now, if we write a KVL equation in this loop, what do we get? We get minus VDC by 2 plus VDC by 2 minus VU minus VL is equal to 0. Right? So we go from negative to positive, it's plus VDC by 2 plus VDC by 2, plus to minus is negative minus VU minus VL is 0. And this gives us this equation. So the net voltage VDC is equal to the sum of the voltages generated by the upper modules and the lower modules if we want to limit any short circuit current flowing through here. So if we follow this equation, at any instant of time, we want the net voltages that is synthesized at the output of the upper and the lower arm to be equal to VDC. So doing so, if each capacitor voltage is Vc, so we have n such modules. So we have n by 2 here and we have n by 2 here. So each capacitor voltage during before pre-energization is going to be Vc is going to be VDC by n, since we have n such modules. But now to operate the MMC and generate a voltage at the output MO, we precharge the capacitor voltages to a voltage which is double this value, 2 times of VDC by n. And why we do that? Because the modulation strategy that is followed in this phase shifted carrier always gives the switching signals to bypass half the modules and to insert half the modules. So let me make it more clear. So at So this is one of the switching rule. At any instant of time, among the n sub modules, only n by 2 are inserted and n by 2 are bypassed. So regardless of what the reference voltage is, at any instance, we may have x number of here. So we'll have n by 2 minus x number of modules turned on here. And we'll come to that, how that happens with the phase shifted carriers. But the switching rule always gives the switching signal where we have n by 2 modules inserted. So Vc times n by 2 modules should always be equal to VDC from this expression where VDC is equal to Vu plus VL. So following that, the capacitor voltage should be Vc is equal to 2 by n times VDC. And this voltage is brought to by using a precharge technique. And we'll come to that towards the end of this lecture if we have time. So the precharge technique brings the voltage to this. And then this is one equation which has to be followed. And the output voltage synthesized, VMO, here is going to be VL minus VU by 2. And that is as simple as following 2 KVL loops here and here. So we can write VDC by 2 minus VU minus VMO is 0. And we can write VDC by 2 minus VL plus VMO is 0. Correct? So if I write 2 KVL equations in the upper loop and the lower loop, I get the equation VDC by 2 minus VO minus VMO is 0. And for the lower loop similarly. And if I subtract these two, I get 2 times of VMO is equal to VL minus VU. And we reach to this equation. Right? So the output voltage that can be synthesized is dependent on the number of modules that are turned on in the lower arm and the number of modules that are turned on in the upper arm. And the difference in voltage between the lower arm voltage and the upper arm voltage gives you an estimate of what the output voltage is going to be here. Everyone following? Okay. I take it for a yes. So now let's take an easy example where we have just 4 submodules. So they're just 4 submodules. So for 4 submodules, we have 4 phase shifted carriers. So for an n level voltage waveform, we have n phase shifted carriers. So let's name it 1, 2, 3, and 4. So now every So we have n number of phase shifted carriers in this case, which is 4, and we assign every alternate carrier, one to the upper arm and one to the lower arm. So for example, if this is the first carrier, this is assigned to module number 1. If this is the second one, it's assigned to module number 3. and this is the third one. It is assigned to module number 2, and maybe this is the fourth one, which is assigned to module number 4. So you see every alternate carrier, one is assigned to the top one, the next one assigned to the bottom one, and the next one is assigned again to the top one and to the bottom one, and this continues. So every alternate carrier is assigned one to the top and one to the bottom. And how does it work out? Fine. Following the same example where we have 4 submodules. So these were the carriers that are generated. Now how does the references look like? Maybe I'll draw over here. So over a 60 Hertz cycle where F and 2F, so F is equal to 60 Hertz, we have 2 references. We call it VL star and we call it VU star. And if we assume this is 0 volt and this is VDC volt, so this is VDC by 2. So now if you have 2 references, one which generates the output voltage for the lower arm, which is a reference for the lower arm voltage, and the other one is a reference for the upper arm voltage. And we saw if you have VL star minus VU star by 2, we generate VMO star, which is the actual voltage that is synthesized at the output. So these are the references which are at very low frequency, which is at 60 Hertz. So compared to this, the triangular carriers are at a much higher frequency, say about 5 kilohertz. So the triangular carriers are going to see it as a constant. This is similar as we did in a 2-level inverter. It's just different that we had a single carrier, a single triangular carrier, but now we have n number of triangular carriers which are phase shifted. Correct? Any questions?
No.
Yep.
The inductor that you mentioned in the ARM, I had a question that since the switching is happening very fast, won't the inductor prevent a quick change of current?
Right. That's the purpose of the inductor. So the ARM currents are much smoother. We saw that in the last class when we compared the 2-level with a multi-level waveform. So this is basically that. In a 2-level waveform, we see that the currents are switched. These are the I arm. And in a multi-level waveform, this current is much smoother. So it can be accounted. One reason is because we have multi-level voltage waveforms. So this current is going to be stepped. And then we have the ARM inductor, which further smoothens it out. So this helps in reducing the THD and the EMI issues in a MMC. So coming to the modulation, we have 2 references, both sinusoidal, one for the lower arm, one for the upper arm. And the net voltage difference between these 2 is what it is going to give us the output voltage. So if we look at this, so we can have this as VL star and maybe we'll have this as VU star, right? If we take like one instant of time, because they're going to be more or less constant since this is happening at a frequency, say Fs is equal to 5 kilohertz. And the references are slowly varying at a frequency of about 60 hertz. Now, let's take an example for an instance where the voltage is switching. This is the output voltage waveform. And since we have 4 modules, it switches between 4 different levels. And this is 0. This is say VDC by 4. This is VDC by 2. Sorry. Okay. Right. So one more thing that I should have noted is that VMO voltage can go from minus VDC by 2 to plus VDC by 2 from this modulation. So in a 2-level inverter, we saw what is the maximum modulation index that can be obtained, the peak of the output voltage to the DC bus voltage. In sine triangle, it's 0.5, and in space vector, it's 0.577, right? So here we're doing sine triangle modulation. We are comparing a sinusoidal reference with a triangular carrier. So it gives us the same voltage magnitude of 0.5. So M is 0.5. And that is why if you have a VDC bus, the output voltage swings between plus VDC by 2 and minus VDC by 2 using the modulation technique. So if we have this, if we try to analyze what happens during this instant, we have the triangular carriers, and again let's call this 1, 2, 3 and 4. This is MO, and we have maybe this reference as 1, this has 2, and similarly this is for the this is for the second module, this is for the third module, similarly this is for the fourth module, right? So the upper arm has 2 alternate carriers and the lower arm has 2 alternate carriers, and we see these are phase shifted, right? So this starts from here, this starts from here, so they're phase shifted by an angle which is 360 degrees divided by 4, right? So we equally phase shift it, and this corresponds to TS by 4 in time, right? So the 4 carriers are phase shifted, and we assign 2 of them to the upper arm and 2 of them to the lower arm. Now this is basically VL, VU star, this reference, and if you see this reference, it's going to be VL star, right? So that we can easily see from this picture. So if you are looking at this area, this is similar to somewhere here, right? This instant of time, correct? Because if we do VL star minus VO star by 2, the waveform is going to follow this for the VMO. And at this instant of time, we see that VL star is peaking, it's very high, whereas VU star is very low, right? So we see that here, VL star is very high and VU star is very low. Correct? So now if we compare these references with a triangular carrier, we get the modulating pulses for these modules. And let's take a more detailed look at it in this slide, right? So for this instant of time, if we compare it with these 2 triangles, this and this, it is lower than both the triangular carriers, correct? So if it is lower than both the triangular carriers in the upper arm, both modules need to be bypassed, correct? So in the upper arm, we say module 1 and module 2 are both bypassed. And do you follow that? Because that's the main crux of the modulation technique. So during this instant of time, the reference is lower than both the triangular carriers for the upper arm modules. So if that is the case, both module 1 and module 2 are going to be bypassed. Similarly, for the lower arm reference, it is greater than both this carrier and this carrier. So we see module number 3 and module number 4 are both inserted, right? Now if these are bypassed, this corresponds to VU star is going to be 0, whereas VL star is going to be twice of VC, where both the capacitor voltages are inserted, because each capacitor voltage is VC. So if we do that, this is going to be, okay, and VC is going to twice divided by N is 4 times VDC, which is VDC by 2. We saw this relationship in the last slide. So each capacitor voltage is going to be twice VDC by N. So each capacitor voltage is going to be VDC by 2. So if we do that, this is going to be twice VDC by 2. VDC, right? And then VMO is going to be VL star minus VU star by 2, which is VDC minus 0 by 2, which is VDC, correct? And that is what we see here. Sorry, VDC by 2, right? And that is what we see here. So this is VDC by 2 and this is VDC by 4, right? Is it a bit confusing? Yes. Yes? Okay. Let's take a look again. So what we are analyzing is this instant of time, right? So as we see, this is the sinusoidal reference that is to be generated. And this jumps between 4 different voltage levels because we have 4 different modules. So depending upon the number of modules, we get the number of levels. So at this instant of time, the voltage is jumping between this level and this level. This is one level and this is one level, right? So it is jumping between VDC by 4 and VDC by 2. And why that happens? That happens depending upon the reference comparison with the triangular carriers. So let's analyze why it jumps between VDC by 2 and VDC by 4. And this is the zoomed out version of that. This is the zoomed out version of this, right? So we have PWM happening inside this thing and it jumps between VDC by 4 and VDC by 2, right? And that is what we're trying to analyze in this slide. So we have the zoomed out version of the triangular carriers with the references and the voltage that is generated. And as we saw, we have 2 triangular carriers here and here, and this is the reference. And this is VU star. Similarly, this is the reference and this is VL star, right? So we see VU star is lower than the triangular carrier here and here. So it is lower than both the triangular carriers. That means both the modules in the upper arm are going to be bypassed, right? So if a triangular carrier, if a reference is more than a triangular carrier, we turn the switch on, else we turn the switch off. It's similar as we do in a 2-level inverter. If a reference is more, we turn the switch on. If a reference is lower than the triangular carrier, we turn it off. Similarly, here, instead of switches, we insert modules or we bypass modules. So now the reference is lower than both the upper triangular carrier and the both the triangular carriers in the upper arm. So both the modules, module 1 and module 2 are bypassed. Now if both the modules are bypassed, we have the upper arm voltage is equal to 0, right? Because none of the capacitor voltages are inserted. For the lower arm, here we have the reference is more than both the triangular carriers. So both the capacitor voltages are inserted. So we have module 3 and module 4 are inserted, right? So the lower arm voltage VL star is going to be twice the capacitor voltage since we have 2 modules, and that is going to be VDC because each capacitor voltage is VDC by 2, right? So that gives us the output voltage VMO by this expression VDC by 2, and that is what we see here. So for this instant of time, which we call T1, so everything is for T1 duration. For T1 duration, VMO is VDC by 2. Now let's see another instant of time, say T2, right? What happens in T2? In T2, we see that the output voltage is VDC by 4. But how does it come from the carrier and reference comparison? So again, this is the reference. Is it lower or higher than the 2 carriers? Lower. It's lower than the 2 references. So again, for this instant of time, we have module 1 and 2 bypassed. Correct? Now what happens here? It's lower than this carrier, but it's higher than this carrier, right? So we have module 3 is bypassed, but we have module 4 inserted, right? So in the upper arm, the net voltage VU star is going to be 0 because both the modules are bypassed. Whereas in the lower arm, one is bypassed and one is inserted. So we have the voltage is just VC, which is VDC by 2. So let me write for T2, we have VU star is 0 and we have VL star is VC, which is VDC by 2, right? So again we have VMO is VL star minus VU star by 2, which is VDC by 4, correct? So Is it clear? So you see, the phase shifted carrier modulation is intelligent enough to give you a stepped voltage depending upon the number of modules. So if you have more number of modules, you have more number of phase shifted carriers. So the number of carriers, number of modules, the same number of carriers, and the same number of voltage levels in the output. Now this is another case where we are jumping between this and this, between voltage levels 0 and minus VDC by 4, right? Correct? So now at this instant of time, if we compare here, so this is the instant, right? Because we are comparing this part. So again, we have VU star here and VL star here, and that is what we get here. So this and this is the reference. So this is VU star, this is VL star. Correct? And again, if you do the comparison for the same instant of time, this and this, we are going to see that it is jumping between 0 and minus VDC by 4. And I leave it as an exercise for you guys to test it out at home, since we don't have that much time. But this is how the phase shift modulation works. We have a number of phase shifted carriers. We have two references for the upper arm and the lower arm. And then we find the number of submodules that are inserted. We saw that from the switching strategy. If we turn the upper switch on, the module is inserted. And if we turn the lower switch on, it is bypassed. And doing that, we get the modulation for the entire multi-level converter to synthesize an AC output voltage.
Question.
Sure.
So between M and O, is that your load then?
Yep.
Okay.
So it can, for a HVDC station, it is going to be a grid, right? Because we have an AC grid and you have a big DC bus. So you have the AC grid with a small grid inductance and resistance. Then you have the MMC converter and you have a DC bus. Now this is analyzed on a single phase basis. So you need a return path. So we have the return path as the midpoint of the DC bus. So for a three-phase system, this entire thing is going to be repeated 3 times. And you have the 3 references which are phase shifted by 2 pi by 3 and 4 pi by 3. So the analysis is going to remain same for a 3-phase system, except the reference is changed by a 120-degree phase angle. But understanding the modulation is much easier when you do a single phase analysis. Right? Now, this is just the simulation results for an 8 submodule case. So you see the output voltage waveform VMO has 8 voltage levels, and then you can count the 0 level, and this is a 9 voltage level waveform. So this is including 0 level, right? So I have 8 submodules, so I have 8 voltage levels from VDC by 2, VDC by 4, and so on. And then you have the 0 level. So in total, you can count this as 9 voltage levels. Now, a major challenge in this multi-level voltage waveforms and the multi-level converters is the capacitor voltages. Now you see, we have a capacitor here, and we assume that this voltage VC remains constant. But we don't have a battery there, or we don't have a DC source there. So how do you ensure that these capacitor voltages remain constant when you're doing the modulation throughout and generating a sinusoidal output voltage? So if we take everything ideal, where all the capacitors are equal, all the voltages initially are equal, we see that they are all constant across the nominal voltage, which is say 125 volt here for an 8 submodule case with a small ripple. Now this ripple depends upon the capacitor value. So the larger the capacitor, ripple is going to be smaller, and smaller the capacitor, you are going to have a huge ripple in the voltage of the capacitors. But then what happens if you include some non-idealities? So if these capacitors are equal and the initial voltage are different, or say Ci is not equal to Cj, because all the capacitors generally have a small tolerance value. We have like 5 to 10% tolerances in the capacitors. So if you have a small tolerance or a slight change in the voltage of the capacitors, we see this is the capacitor voltages. So they're totally unbalanced. So if our assumption that VCI is constant is no longer valid. And if we remove that approximation, the modulation is not going to happen correctly, because the voltage is synthesized depending upon the number of submodules that are inserted. Now, if the modules that are inserted don't have a voltage which is same, the output voltage is going to jump up and down, like it's jumping up and down here in the modules. Now, this calls for a control technique which is going to balance these modules. And I think we'll not go into detail into that because it's going to get a lot more confusing and we don't have enough time. But this thing is going to turn into this, where we're going to sense these capacitor voltages and send it to a controller. So for number of modules, we have the same number of voltage sensors. So in a simple thing, what we do is we have a modulation block. We get a VU star and we get a VL star here, right? And these are the carriers. We have the phase shifted carriers. Now this generates the switching pulses SI for the modules that are going to be inserted or bypassed. Now, regardless of which module is turned on in the upper arm and the lower arm, as long as we maintain the number of modules that are turned on, the modulation is going to happen, right? So in the last example, we saw that one module in the lower arm is turned off and one is turned on. Right here, right? So during this instant, we saw module 3 is bypassed and module 4 is inserted. Now what happens if we say module 4 is inserted, module 4 is bypassed and module 3 is inserted? Nothing is going to change, right? The output voltage is going to remain the same. So what we do is we sense the capacitor voltages of module 3 and module 4, and depending which capacitor has a lower voltage, we insert that or we bypass that, depending whether it's going to be charging or discharging. I mean, let me make it a bit more clear. So after this, we have the voltage balancing block. Now this senses all the capacitor voltages, and this also senses the arm current direction. Now the arm current is basically what is going to charge your capacitors or discharge your capacitors, depending on its direction. So depending on this arm current direction, we know whether the current is a charging current or discharging current. And depending on the modulation, we know how many modules to insert. So we take into consideration the capacitor voltages, the arm current direction to decide whether we should insert module number 3 or we should insert module number 4. And that is what the balancing block does. So the algorithm is here, might get a bit confusing, but I'll try my best. So let's take one example where
Zoom into that block. Can't see anything here.
It's not in my control. But could you please zoom in on this thing?
Thanks.
Yep. Okay. So the upper one is to add a module. So here we are adding a module, and this way we are removing a module, right? And this adding a module and removing a module comes from the modulation block. So suppose the modulation asks us to add a module. So we go here in this algorithm, we measure the arm current direction, right? This is IA direction. And this thing repeats for the upper arm, lower arm independently. So let's take the same example that we had for the lower arm, where we had to turn on one module, either it is module 3 or module 4, and bypass one. So here we measure I lower direction, right? And depending whether we have a charging current or discharging current. So this is a capacitor, right? Now if the current is going here, IL, in this direction, it's going to charge the capacitor, right? But if the current was going in this direction, let's call it IL dash, it's going to discharge the capacitor, right? Correct? That's the basic thing for a capacitor. So if it is a charging current, we move here. Now what do? We find the module which has the lowest voltage and turn it on. So we have to insert a module, whether it's S3 or S4. Suppose we see that S3 has a lower voltage than S4 and we have a charging current. So we turn on S3 instead of S4. Does it make sense? So we are turning on that module which has lower capacitor voltage and we have a charging current. So the modulation strategy, the voltage balancing strategy basically takes into consideration the arm current direction to decide whether it's a charging current or a discharging current, and then it takes into consideration the capacitor voltages which have the lowest voltage or the highest voltage. So if it has the lowest voltage and it is a charging current, you should turn that capacitor on because it is going to charge that capacitor to its nominal value. Whereas if you have a discharging current, as we see here in this direction, we should find the capacitor voltage which has the highest voltage because it is more than the nominal and discharge it so it comes to the nominal value again.
Like, what percentage of switching loss? How much does this add? Because it seems like you're switching these IGBTs quite a bit extra.
Yep, it adds to switching losses, but then it has much more advantages as compared to a two-level converter. You have lot many switches here, so of course you'll have lot more switching losses, but then you get a much improved harmonic spectrum at the output. So you reduce the filter requirements. But yeah, the modulation and control is much difficult here as compared to a two-level inverter. So there are complications, but this topology has been implemented and it is the state of the art today. So any more questions? Yep.
The sensing of the current and voltage, how has it performed in hardware? Like, do you do a simple step down? And
you can use any sensor that you feel right. I'm not sure what they use in the industry, but in the lab we use Hall effect sensors. Right? So it's in the closed loop fashion where you sense the current direction, you sense the capacitor voltages, and you do the actual modulation to get the switching signals for the converter and synthesize a stepped output AC voltage.
Can you just repeat why there is a discrepancy in voltage levels in capacitors? I mean, you showed a graph, right? I mean,
Sure.
capacitors at different voltage levels.
Yep.
I mean, can you tell
This one?
Yeah. Can you tell again why the reason is? I mean.
Okay, so you are switching on the converter. You are switching the converter on and off all the time, right?
Yeah.
So your modulation algorithm tells you to turn on 2 modules and 1 module. But these capacitors are floating, so they have an initial voltage which is through a pre-charge technique. But then depending on the modulation, whether you charge it or discharge it, these capacitors are going to sway up and down, right? And if everything is ideal, like we saw on the previous slide here, where all the capacitors are ideal, all the initial voltages are ideal, we are going to see that they are all going together, right? With a small ripple, which is dependent on the capacitor voltage. But then if you have some non-idealities, the capacitors available in the market have a tolerance of 10%. So one may be one of the capacitor may be 1.1 per unit, the other one can be 0.9 per unit. So the amount it is charged during one cycle may not be the same as it is charged by another capacitor in one cycle. So we see all the capacitors can sway up and down. Now if all the capacitors are going diverging, there are different voltages. This is the voltage that is going to be used to synthesize the output. So the output voltage is going to jump up and down and you won't get a near sinusoidal voltage. So that increases the filter requirements and causes stability issues in the system. Right? So any more questions with the voltage balancing? We are doing a lot of stuff in a very short interval of time, so we'll try to keep it simple in the exam maybe.
Actually, so this topic is not on the exam.
This topic is there. The one which is covered next week is not.
Oh, okay.
That is why I said good luck at the starting. Okay, so here we see there was a disturbance in the capacitor voltage here and there is no balancing. So this is with no balancing. So we see the capacitor voltage sways and doesn't come back. Whereas here, when we have balancing, this capacitor voltage goes and merges with the other capacitor voltages. So this is basically the capacitor voltage algorithm implemented. And similarly here, so the pre-charge was done to a different voltage here for one of the capacitors, and others all started at the nominal value. So this comes and merges with all the other capacitor voltages because of the balancing algorithm. So basically this shows that. Now these are just the voltages and currents. Different submodules, I don't know how far we cover, but what we talked about so far was the simple half-bridge submodule, which is this. This is the most conventional. And this is what has been implemented by Siemens in the Transbay cable project that Professor showed last time. But we also do have other submodules, which is the full bridge, where you have two IGBTs, and this is the terminal. So we have A and B, and we have the capacitor in between. Right? So it's just a half bridge multiplied by 2 with a common capacitor. And these are just other topologies, clamp double, and these are derived from multi-level, which we see next week, neutral point clamped and flying capacitor. So these have been in research but have not been implemented. The full bridge is being seen by Alstom for implementation in an HVDC project, and this has the added benefit of DC fault handling. And I don't think we have that much time, so we'll just say this is used for DC. Right? And these are the operating states. We'll not go through this. So it just has an additional state of minus VC instead of VC and 0. And this state helps in fault handling. And maybe we'll skip all that. Now I talked about that all the capacitors have to be pre-charged to the nominal value of twice the VDC by N, and we have some pre-charge techniques for that. So cascaded charging is basically sequentially charging one of the capacitors, then the other, using an external DC source. So this is called sequential charged. Parallel charging is where we have a DC source and we charge all the capacitors at once, and then once the charging is done, we remove the DC supply. But then this is one of the intelligent charging techniques where we charge it using PWM, pulse width modulation, and this doesn't have any overcurrents, no overcurrents, and is the preferred method of doing, but we're not going to go into details because we don't have enough time. And basically, well, that's it. So any questions? So I think in this part, we're just going to focus more on the modulation part, if at all we have any questions on the exam. And I think we'll skip the voltage balancing, maybe, but that call rests with Professor. And hopefully we'll have a few homework problems so that you guys could practice. Well, thank you.
Okay, so thank you very much for sticking with the material so far. We will take a short lunch break and we will resume at 1 p.m. Central Time. The agenda for the afternoon session is as follows. Dr. Siddhartha Raju will present the material that he has prepared for the new labs. Although the labs themselves are not ready yet, we have the labs for the drives course all ready to go. In fact, it's already been offered once here. And then I will talk a little bit about the material that I have prepared on EMI and EMC with respect to power electronics and converters. And so we expect to finish that within about 3 hours. So we wouldn't want to keep you too long this Friday afternoon. So we'll be back at 1 p.m. Central Time. So until then, please feel free to have your lunch, and then we'll resume at 1 p.m. Thank you. me enable video here. So welcome back to the afternoon session on this third day. This is the final session of this 3-day workshop. Thank you for sticking with us through this long session. What we're going to do now is Dr. Siddharth Raju is going to take over, and he's going to introduce the platform, the SciAmble platform that he has developed, and in relation to the power electronics lab that is being developed. And he will also talk a little bit about about the drives lab that has already been developed and has already been deployed at UMN. And following that, then I will talk a little bit about the module on EMI and EMC. So I will now hand over to Dr. Siddharth Raju.
Thanks, Abhi. Hello all, I'm Siddharth. I'm a postdoctoral fellow at Professor Mohan's laboratory. And as Abhijit mentioned, I'll be initially talking about the power electronics lab that we have already been offering here at the University of Minnesota. And this lab has been offered for like around a decade and a half now. And we are going to be updating it to a newer system. And I'll be talking about that too. And then finally, I'll show like a brief demonstration of the electric drives lab that we have already developed. Okay. So this is the power electronics board that we currently offer. It's being sold by a company called Hydel, which is a subsidiary of Vishay. And this lab, this hardware basically has a switching power pole to switching power pole. And you can plug and play different modules onto this board to make it do different kind of experiments. So you could do buck converter, boost converter, forward converters, flyback, all of this in the single board. And it's, as I mentioned earlier, it's currently being sold by a company called Hyrel. And this is the board. On the left, you can see the two switches and the diode. And depending on what converter you want to run for the lab, the configuration can be modified. And on the top, you see the plug and play board. For this particular experiment that I'm going to initially show is the buck converter. So we just plug in the inductor. But if you want to do a forward converter or any other different converter, different plug and play boards just come into this particular board. So these are the list of experiments that we usually offer every semester for the power electronics lab. And these are the buck converter, boost converter, buck boost, and the switching characteristic of MOSFET. And then the current mode control and voltage mode control. And then we have the flyback and the forward converters. So initially, I'll show you the first experiment that we do, which is the buck converter, which is the most simple experiment. And later, I'll show an experiment on forward converters. And rest, you can download the manual available online and buy the hardware and do it yourself. So everybody knows the schematic of a buck converter. It's just a switching power pole, a switch on the top, a diode to freewheel on the bottom, and then an inductor to filter out the current, and then the capacitor, and you have a load. So this is the hardware. So the rheostat is being used as a load in this this experiment, and you configure the board as given in the manual so that it operates as a buck converter where only the top switch is being used and the bottom diode is being used for freewheeling. And this is the output. These are the output waveforms that you get when you run that experiment. You can adjust the duty cycle of the converter as shown here. You can just adjust the knob, the duty cycle knob, and change the duty cycle anywhere from 10% to 100%. And you can control which of these two switches get the gate signal. If you drive the gate signal to the top switch, it operates as a buck converter. If you drive the gate signal to the bottom switch, it becomes a boost converter. And the rheostat that you see on the right corner allows you to control the frequency, which can go anywhere from 10 kilohertz to around, I think, 120 kilohertz. So in this experiment, we have kept the frequency a constant of around 110 kilohertz. And then we adjust the duty cycle from 10 to 0.1 to 1. And we can see the output voltage and the currents and the switching voltage magnitude change. So in this waveform, the purple color, the channel 3 is basically your switch output voltage, VA, and your blue is the capacitor output voltage across the capacitor output capacitor, and then the dark blue, and then your light blue or cyan would be your the aqua color, that's channel 2 would be your load current. So as you can see, as you increase the duty cycle from 10, 15, 20, you can see the voltage, output voltage across the switch VA increase, the duty of it increase, and then the output voltage, which is the channel 1, increase. And you can see the ripple, the output load current also increase. And if you notice at 50%, you would have the maximum peak-to-peak ripple current, as you can see here. And then as the duty keeps increasing, the ripple current keeps coming down, but the current magnitude itself goes up, the average current. So this is the first part of the experiment that you can again download from the CUSP website, the Power Electronics Lab Manual. So that's in continuous conduction mode, where if you see the current, that's the channel 2 value, never goes to 0. The lowest duty cycle at 10, it almost approaches 0, but it never goes to 0. And that's called continuous conduction mode, when the load current doesn't go to 0. And it's usually preferable to operate in this mode. So there are certain applications where you don't do that. But in buck converter, it's usually preferable to operate in this mode because it's possible to control predictably the output voltage. If you go to discontinuous conduction mode, depending on the load, the output voltage magnitude starts to change. And it's not only dependent on the duty cycle anymore, but also on the load and other parameters. So this is the output voltage in discontinuous conduction mode. So this is the boundary of continuous and discontinuous. And once you start going to discontinuous conduction mode, you can see the current, which is a channel 2, almost be 0 for a small period of time. And as the amount of time the current remains 0 increases, you can start to see the switch voltage has 3 distinct level. In continuous conduction mode, there were just 2 levels where if the switch is on, the output voltage is going to be the voltage across the switch node, and the common is going to be Vm, which is 20 volts in this case. And if the switch is off, then the diode is going to freewheel and your voltage is going to be 0 or 0.4, the diode voltage. When you have discontinuous conduction mode, you'll have 3 distinct voltage levels: the 0 when it's freewheeling, the input voltage when it's conducting, and then the output voltage when it's freewheeling, but the current has died down to 0. So the oscillations that you see here are due to it. If there were no parasitic elements, the voltage would be a flat voltage. So the oscillations that you see, they would have ideally settled to whatever the channel 2 voltage was, the dark blue color. But because of the parasitic capacitance across the diode, the freewheeling diode, you would have an oscillation. It's basically a DC step voltage across an LC, and that causes oscillation that you see here. So in a buck converter, this oscillation is not a significant issue. It adds on to the losses, but it does not cause any device failure as such, because this oscillation is going to be at the max 2 times of your output voltage. And if your output voltage is within 50%, you would still be within your input voltage peak. But if your output voltage, say, is if your duty cycle is 100%, then you could go all the way up to input voltage, and then your oscillation would be 2 times the input voltage. So as long as your device is rated for 2 times, you would be absolutely fine. But this would not be the same case with boost converters, where the output voltage could be significantly higher than input voltage. So these kind of discontinuous operation would cost 2 times the output voltage, which could potentially damage your switches. One way to remove these kind of oscillations from your output voltage is to use snubber circuit across the diode. Put a damping resistor in the snubber circuit, and the oscillation would die down pretty quickly, or it won't reach to the significant magnitude to damage the device. So this is the second part of the buck converter experiment, and that would conclude the first experiment in the basic drives manual that you can download from CUSP website. So the other experiment that I would like to go over today before finishing this part of the segment is the forward converter. This is the last experiment in the Power Electronics Lab Manual. So forward converter is pretty straightforward. It's similar to a buck converter, except you get isolation with it. So you just put a transformer in there. There are certain limitations because of the presence of the transformer. The transformer here, because of its operation, there are certain limitations on the duty cycle. In a buck converter, the duty cycle can go all the way from 0 to 1. But in a forward converter with 1:1:1 transfer ratio, your duty cycle will be limited to 50%. And we'll see the reason as to why later in this experiment. So the converter itself is quite straightforward. So you the transformer, think of it like an pretty much an ideal transformer. So you can the switch voltage, whatever is going to be across plus V1 is going to get reflected across the winding N2 when the switch is on, and when the switch is off, the current that was the magnetizing current that was flowing through winding N1 needs to be discharged out, or else you'll interrupt current through an inductor. So we have the diode D3. So whatever magnetizing current was established when the switch was turned on is now the energy is fed back into the input power supply through winding N3. But other than that, the rest of the circuit is pretty much similar to what you would get with a buck converter. So going back to the hardware, for the buck converter, we just had like a simple inductor board which was on the plugged into the top. We replaced that with the forward converter Magnetics, which basically is the transformer that you see here and the inductor on the right side of the converter. So those two elements combined, the transformer is in the bottom and the inductor is on the top. You can just use this other plug-in play board that you can just put in, and the whole converter would operate as a forward converter. And if you see, the wiring also has been changed a little bit so that these switches are reconfigured in such a way that it operates as a forward converter, but the board is still the same though. So similar to the buck converter experiment, the first part is you're going to operate it in continuous conduction mode. In buck converter in continuous conduction mode, there were two distinct voltage levels, which was the Vin and Vo across the switch. In this case, there would be three distinct voltage levels depending on because there are three different states that occur in a forward converter, and we should just go over them briefly here. Again, the purple or channel 3 is your voltage across your switch, and channel 2 is your output load current, which is the aqua color, and then the green, which is channel 4, is your input current, and blue is your output voltage, which is channel 1. So here we have a duty cycle of around 30%. So when the switch is turned on, the channel 3 voltage goes down to 0. Which is the voltage across the switch. So the voltage across the switch goes down to 0, which basically means the output inductor is going to get charged up. So you can see channel 2 current ramp up from almost 0 to its peak value. And you can see the input current, which is in channel 4, ramp up proportionally. The winding is 1:1 transformation ratio. So and the duty cycle is almost approaching 50%, which is around 30-40. So the input current would pretty much be almost close to the output current. So you can see the input current also ramp up proportionally, almost proportionally. And when you turn off the switch, the output voltage, when you turn on the switch, the switch voltage became 0. When you turn off the switch voltage is going to become the input voltage, which in this case is 20 volts. And you can see the output current gradually ramp down because it's getting the energy stored in the inductor is being pushed out into the load, pushed out into the capacitor, which is then discharging it into the load. So the current starts to die down. And if you look at the input current, which is channel 4, which is green color, you can see there is a negative current flowing. So this is basically the current that is coming from the diode. So whatever current was established, the magnetizing current established by turning on the switch, that current needs to now die down. Basically, the energy stored in the magnetizing inductor needs to be discharged back into the source. So there is a reverse current flowing back into the source. So that is the negative current that you see. So, and this voltage would remain there as long as the magnetizing element still has energy stored in it. And once that current gets discharged out, you can see the input current goes to 0, and then your output voltage, your switch voltage would settle down to your output voltage. So this is in the continuous conduction mode. And as you keep increasing your duty cycle, you can see the output voltage increase proportionally. They must be so this middle interval that you see there in the third channel, that cannot go to 0, because that is if that goes to 0, your magnetizing inductance, the energy stored in the magnetizing inductance is not discharged fully before the next cycle turns on. So this could be disastrous because this could lead to the transformer to saturate. So you want the magnetizing element to charge up during the switch turn on. And when the switch turns off, you need to discharge it fully before you can go on to the next cycle. If not, there would be a residual magnetizing flux in the core, and this keeps on building up, and the core would saturate, and it could potentially lead to very high currents. If there is no current limit, it could damage your whole circuit. So that's the limitation. That's the reason why the forward converter has a limitation on the duty cycle. For a 1:1:1 transformation, you would get a limitation of 50% duty cycle, because above 50%, the amount of charge, the time available for charging would be higher than time available for discharging. So there will be a residual buildup of the flux in the core. So this is at the very edge of allowed limit, where the magnetizing energy is just barely discharged. This is a continuous conduction mode because the load current never went to zero, absolute zero. So the second part of this experiment is the discontinuous conduction mode, where we allow the load current to go to zero. And similar to whatever happened in buck converter, the same phenomena is going to happen. You're going to see an oscillatory output voltage, voltage across the switch, because of the parasitics formed by the diode, in this case, as well as the parasitic capacitance of the transformer. So the energy stored in the inductor, energy stored in the capacitor, output capacitor is going to now oscillate between your filter inductance and your parasitic capacitance and of the diode as well as your transformer. And that is the voltage that you see, a little bit of oscillation. Ideally, if there was no parasitic components, the voltage would settle down to your output voltage, the intermediate, once the inductor is discharged. But due to parasitics, you see a significant amount of oscillation. And again, similar to buck converter, you can reduce these oscillations by simply just adding a snubber circuit with a resistor in it. So this is what would happen if you push a forward converter beyond 50% duty cycle for this particular case of 1:1:1 transformation ratio. The 50% duty cycle would not be the case if the transformation ratio is different. It's a function of the transformation ratio. So if you do not allow sufficient time for the current to discharge, as you can see in channel 4, the negative current never goes to zero, before which you turn it on and push the current again. At this point, your transformation ratio would no longer work. In this board, there is current limit, so it does not damage the board. But your duty cycle transfer function will no longer work because your transformer is not functioning as it's expected to function, because it has already saturated due to the residual flux that keeps on building up. So this is the power electronics lab that we have offered so far, and all of the control on this board is analog. We have like a 555 timer or similar ICs to do the PWM generation, but for the most part, it's you use the rheostat to change the duty cycle, change the frequency, and all those stuff, and it's completely analog. And as I mentioned earlier, this lab was developed like a decade and a half back, and we are in the current iteration of trying to update this so that we can make it digital. So in the next revision of this power electronics lab that we plan on offering, we are going to be making it completely digital and coupling it with our software that we have developed to be able to model power electronics and electric drive system. So we are going to retain the same power electronics component as the previous version, but we're going to add a Texas Instrument DSP on board so that we could do all form of digital control, add more experiments, do closed loop control, do controller design, and add those as well as part of experiments in the power electronics laboratory. This is the overall circuit diagram of the new lab that we are going to that we are designing right now. And our plan is to offer two different variants. One is using silicon, and the other one is using GaN. Both of it, so that all the experiments that have already been developed and are being run using the current setup can be run on using the GaN hardware as well. It's exactly the same, with just the difference being that we have a digital controller on top of the board that you can control. So again, the same board can be configured into multiple converters, as you can see here. Just changing which switch that you use, you could use it as buck converter boost, synchronous buck boost. And what I haven't shown here is the flyback forward converters, the full bridge converters. So all those could be implemented as well using the same board. So the last part of this presentation, I would like to talk briefly about the software that we have developed to be able to do power electronics and drive simulation. So right now we are offering this solution mainly for electric drives laboratory. Again, the previous electric drives laboratory was designed, I think, about a decade back, and we revised that so that it's no longer dependent on MATLAB and DSpace that we used to use before, which were quite expensive. So we moved on and we created our own numerical simulation software called SciAnvil Workbench, and it's available completely free for anybody to download and use it. And one of the advantages of using this software is that it couples with all our hardware directly. So you don't need to know any C programming or any coding to be able to jump right into doing any form of control, motor control or power electronic control. It's all drag and drop model based design that you can just connect them up and simulate your system and then immediately port it onto a hardware and then on the hardware as well. So the schematic that that you see right in front here is a basic buck converter control. So you have a slider to control your output voltage, and you scale the output voltage by 1/2 VDC and then add 0.5 to generate the duty cycle of the top switch, and then subtract it from 0.5 to generate the duty cycle of the bottom switch. So this is one of the simple experiments in the electric drives lab to show an operation of a full bridge converter. And later I will show you a video of an actual vector control of an induction motor running to demonstrate the capability of this software. And as I mentioned earlier, the software is completely free and anybody can download it and use it. And and they could make their own labs too if they want. There are no restrictions on how you get to use the software. So this is the one of the experiments that we designed for electric drives lab, which is a vector control of an induction motor. This is the I think the first experiment in the advanced electric drives lab, which is a graduate level course that we offer. So we have an induction motor model which we want to control the speed of, and then we have a DC motor model which emulates a load. And our aim is in our lab to show design a PI controller so that irrespective of what load conditions you put the motor to, the speed always settles down with certain transients which have a profile that's of particular interest. So if you want to overdamp system, you choose certain PI values. If you want underdamp, you choose certain PI values. And the whole lab is designing the whole motor model in DQ, and then designing the controller, simulating the system, and then running it in real time and verifying if the results match exactly. So this whole system is designed using this Workbench software. And here's a brief video that shows the software in action. So, and yeah, I'll just load a previously developed induction motor model. So as I mentioned earlier, the model lets you to control a real-time hardware without having to do any sort of programming. So as you can see here, I would use this model on the left to control the actual hardware. So what you see on the right is the power electronic, is the electric drives hardware, which has three phase inverters inside it to be able to control 3 different motors independently, or have a DFIG control the stator, rotor, as well as a load, all of them using that single unit. And in the system, what we have right now is an induction motor, which is coupled to a DC motor. And as you can see, once I run this model, and once the motor starts rotating, the speed data would start coming back to the scope. And again, all of this is interfaced in the backend, and there is no programming required from the user end. So as the motor speed rotates, you can see the speed being logged into the plotted on the software scope. So in this experiment, what we basically did is give a step response, step speed request, and then step speed command. And you can see the speed settle down at whatever the required speed was. And this is an underdamped response. And in the lab, we asked the students to change the PA values so that to make it from underdamped to overdamped, change the values. And at about 3 seconds, if you see, you can't see it pretty clearly, but there is like a small dip. That's when the DC motor emulates a load and adds a load onto the system, and you can see the speed dip. And if your PA controller is designed well enough, the speed should kind of recover and come back and settle to the expected or desired value. So yeah, this is the blown out scope. And as you can see at 3 seconds, there's a small dip that I mentioned. So the whole system can be, again, these are different scopes. results, currents in the flux. As I mentioned earlier, the same system can be simulated as well, so you don't need to use any other software to run the simulation. So both simulation and hardware, you can just do it using a single system. As you can see here, I just simulated the result, and you can jump back and forth between the simulation results and the hardware results. So what I was showing there was basically the speed response. You compare a simulated model speed response versus what you get in the hardware. And this lets you see if you have estimated your parameters correctly, or if there is some things that you haven't anticipated in the hardware to occur that you haven't modeled in your system. So for instance, if you haven't accounted for the frictional losses, as you can see here in your simulated system, your estimated torque and your actual torque are exactly the same. But in your actual system, you can see a small discrepancy because the simulated model does not have a frictional model, a viscous friction model. So you see a discrepancy. And then you can go back to your simulation model and compensate for the discrepancy so that the simulation model and your hardware models match exactly the same. So our idea is to extend this software to the power electronics lab as well, and start offering it fall of 2020, so that you could use the same simulation software to simulate your power electronic models, and then use the same software to control your power electronics hardware as well for your labs. And yeah, with that, I would like to conclude my presentation. If you have any questions, I would be more than glad to answer. Thank you.
All right, thank you, Dr. Siddharth. We'll wait a few minutes to see if there are any questions. I think there's a lot of material that was covered in this class session. The software is available online, as he has mentioned. What we will do is, of course, this recording will be posted online along with all the other sessions after this workshop in a few days, and we'll make these slides available in PDF form as well. What's a good place for them to go and get the software, look at the software?
So they can download it from sciamble.com. So it's sciamble.com.
All right. So anyone who wants to take a look can go to sciamble.com, and you have some demos and you have some models there as well. Yep. So you can go take a look at those.
Yeah, or they could like shoot an email to either professor or you or me, and we could reply back with full details.
Yeah. And so how many universities so far have started using the Drives Lab?
So around 13 universities have bought the Drives Lab so far. We have been offering it for like 8 months now.
Okay.
And we haven't like publicized it. We're just kind of doing like a beta testing. So.
Right. Okay. So any other questions? Please post them to the chat box that you see on the right. And if you have any questions, as he said, you can send an email to either Professor Mohan or me or Siddharth, and we'll try our best to reply and get to your answers as soon as we can.
All
right.
Thank you.
Thank you, Siddharth. So that brings us to the final segment of this workshop, and I will be presenting a little bit about the EMI EMC module. So it's been a long 3 days. I don't want to bore you all too much. So what I will do is I'll keep it really brief. I will walk you now through the content, and then we'll watch one video module, and then we'll discuss the problems and some of the numericals that I did in class. So I will just share my screen here. Okay, so these are the slides that I had used for the module on EMI and EMC, specifically for power electronics professionals. The original intent was that this became a part of the course that was taught here in class in spring of 2017. And then eventually we sort of condense that material down into a 3-lecture series of half an hour or 35 minutes each. The way the material is organized is as follows. The first part is a review of basics, just fundamental concepts, and a review of things that are needed for students to appreciate what's going on. This is, again, 2 parts. The first part is just an overview of what EMI and EMC is, the various facts and figures surrounding it, the different standards. And then in the second part, we do a little bit of review of electromagnetics, some circuit theory, and so on. And then in the second part, instead of tackling various arbitrary imaginary constructs, we dive straight into case studies, because we feel that it's easier to understand topics, understand these concepts, looking at real world examples. So we dive right into specific cases, and then we examine EMI issues or problems in each of these. And then in the third part, then we look at some problems, some numericals and things like that, because at the end of the day, again, we need to have some problems for students to be evaluated on at the end of the course. So some numericals and some practice problems are there as well. So my plan for today, this session, is to actually just walk you through the slides for the first part, that is the first lecture, because I don't want to play the video. The video is, of course, intended for students, but it's a little too elaborate, and we can probably save some time and skim through most of it right now. And then for the case studies part, I think it would be good if you watch the entire video. So we'll then watch the second part, which is the full video. And then again, for the third part, again, it's all problems. And instead of watching the entire video, then I will just pull up the problem sheet, and then I will sort of walk through the various problems, what are the concepts that we are trying to convey, and how we plan to test them. So I hope everyone can see my screen here. If anyone has any questions on the way, please feel free to just add them to the, just post them to the chat box, and I will try my best to keep monitoring the chat to answer any questions that may be there as and when I get them. Okay, so just to get started very briefly. I think you lost internet connection. Yes, I think so. Okay. Yeah, I seem to have an issue here. Yeah, something is stuck. Yeah, my Zoom seems to have crashed. Let me just close off all this unnecessary stuff. Actually, nothing else. So you're back. Okay. Yeah, Jara, maybe. Yeah. Okay. So Jara, maybe if you could just keep an eye on your machine and let me know. All right. So I'm sorry. Sorry about that. I'll just start again. So in this first part, what I wanted to do was talk to the students, convey to them what is EMI, why is it important, and how does it really make sense for power electronics engineers, circuit designers, topology designers, control designers to know what EMI is, what regulatory requirements there might be, and why is it important for them to understand what's going on. So that's the first part. The second part is just we dive right into case studies, and the third part we look at problems. So I hope everyone can see my slides now. The first part I'm going to just skim through right now. Then for case studies we'll watch the video, and for part 3 again I'll use the PDF and then walk you all through the document. Okay, so what is EMI and EMC? First, I go into a little bit of terms and definitions. I'm sorry. First is EMI, which stands for electromagnetic interference, and EMC, which means electromagnetic compatibility. These are sort of two sides of the same coin. And then just to elaborate on that, electromagnetic is just sort of recognizing the fact that electrical and magnetic phenomena are sort of intertwined, and one causes the other, and so on. Interference is any kind of hindrance or disruption of intended operation, and it's closely related to noise, which is any undesirable signal or a disturbance that degrades the signal. And when we say compatibility, it means multiple pieces of equipment should be able to operate together seamlessly without any interference or any hindrance or any disruptions. So that's just an overview of what these terms mean. The next thing that I talk about is sources of electromagnetic emissions. So where do electromagnetic emissions come from? So of course there are natural sources like lightning, electric storms, and so on. So anyone who's listening to a radio during a lightning storm or watching television, they know that your signal gets disrupted, or signal loss happens during an electric storm. Sometimes there is a phenomenon called the aurora borealis, which is a result of electromagnetic radiation from the sun hitting the upper ionosphere. That also causes a lot of interference in our electronic systems. Of course, there are unintentional sources of electromagnetic emission, such as power lines, motors, transformers, all these devices that have electromagnetic fields in them, which are necessary for their working, but they don't actually intend to transmit any energy. They just do so unintentionally. And the final source, of course, are intentional sources, which means things like radios or any kind of wireless communication where the intent is to transmit electromagnetic energy. So all of these constitute sources of electromagnetic or EM emissions, and we need to sort of have students be aware of them. So then the question is, why consider EMI and EMC at all? So the first thing, of course, is product functionality. If your product is going to fail in an environment where there is stray electromagnetic energy, of course, it doesn't make for a very good sales pitch, right? You want to be able to sell a product at the end of the day. So that sort of comes into product efficacy, could also affect accuracy and precision of, let's say, a measurement system or a control system, where noise could affect the accuracy and precision of whatever is being measured or controlled. And of course, the final thing is overall quality. You want your product to behave in a predictable, reliable way, despite any ambient EM emissions. The second part is sales. There are some statutory requirements for EMI, EMC compliance. And of course, when we design a product, we want to be able to sell it not only in the current market that we design, but worldwide eventually. And so it's important to think about all these before the product before product design begins. So one of the good rules of thumb is good designs explicitly include EMI consideration and EMC planning from the start of the project, and not as an afterthought once the initial product has been designed or prototype has been made. So And that this is where we sort of highlight that, as power electronics engineers, as switching frequencies go higher and higher, power levels go higher, power densities increase, it's becoming even more important to consider EMI consideration than EMC planning. So just a quick overview of what the regulatory bodies are. Of course, you may want to supplement these slides with your own material or give some specific examples here. Then just a quick point on what is emission and what is susceptibility. Emissions basically means what is the electromagnetic energy that is emitted by a device. And susceptibility is just the other side of the coin, which means what happens to a device when it is subjected to this emitted radiation. So electromagnetic compatibility, which is the standard or the requirement, of course, has both of these included. Depending on the application, depending on the market, there may be different requirements on these two sides. So of course there is a limit on emission, basically which says that you cannot emit more than so much of electromagnetic energy. And susceptibility requirements, on the other hand, are in terms of how well the device should continue to operate despite external EM interference. And then in class, of course, it's nice to keep things real and give lots of examples. So I compiled this list of EMI effects in real products. So that, for instance, there's a very common problem of GSM cell phones. They emit very, very powerful electromagnetic radiation, and the problem is that interferes with a lot of things. So there was this example of a multimeter that gets bricked. It gets completely ruined just by having the cell phone near it. Anyone who used GSM phones long ago next to, say, a radio or an audio player, they know that just whenever the phone communicates with the tower, you get this really bad noise on your audio system. And so there's a list of many other examples just to keep the students interested and give them some practical real-world examples. Then the second part is just a quick review of electromagnetics. Most students if this is a bachelor's level program, they would know most of these if they've covered basic electrical engineering courses in their course, but it's always good to do a quick review. So Faraday's law, Ampere's law, and so on. Then we get to EMI concepts, very specific concepts related to EMI. The first thing that I talk about is a little bit about antennas and propagation. Of course, it depends on whether the students have already had some course in antenna theory, which is not required. But one of the good things to know is this relation between the λ/4 length or feature size and the wavelength of energy that it can emit. So just to give a quick example here, for instance, I take a few frequencies here and I find out what is the wavelength, that is the lambda. And I find out what would be the size of an antenna, of a λ/4 antenna that would be required or that would be able to emit or absorb at these frequencies. So just some few common examples. So 2.4 gigahertz is the wireless band that a lot of cell phones, sometimes microwaves use. So you can see that λ/4 turns out to be about 31 mm. And 31 mm would be maybe the length of a trace on a PCB. Could even be the pin on a connector. So that's a fairly small size. And just to be aware that something that's about 30 mm long could be picking up energy in this 2.4 gigahertz band. The second band is 900 megahertz, which is again wireless communication. A lot of ISM stuff happens here. And in this case, the λ/4 turns out to be about 83 mm. So 83 mm is about 8 centimeters, right? Around 10 centimeters. So this could be, let's say, a wire or a piece of cable that connects to pieces of equipment. Could be even a power supply cable and so on. So that could pick up something in this band. Then we have the longer wavelengths and lower frequency, that's 300 megahertz, again wireless. That turns out to be about 25 centimeters. So this could be, for example, a power cable. So a power cable could be picking up unwanted noise and coupling it into your system. So when we talk about noise mechanisms, there are primarily two noise mechanisms that we talk about here. So one is called inductive coupling and the other is called capacitive coupling. So let's look at capacitive coupling first. Essentially what happens is that in capacitive coupling, a parasitic capacitor is formed, which is between a voltage source, which we call the noise voltage source, and our system, which is of interest, and we call this the victim. Basically, it means that there is some extraneous noise which is negatively affecting our system. So this electric field in the intervening space essentially is forming a parasitic capacitor, which is shown here. This is called C effective. And so this effective capacitor basically couples noise from the noise source into the system that we are trying to protect. And a common example of this is, of course, power lines. So if you have 230 volts or 120 volts wiring in your house, that wire forms one plate of your parallel plate capacitance, and that's at a fairly high voltage, right? So it's at 120 volts, it's at 60 hertz, and if you have let's say you have an amplifier or you have a sensor signal conditioning circuitry, that circuitry forms the other plate of that capacitor, and so you are going to get basically noise coupling, where so your output is going to have the desired voltage as well as some of this coupled voltage. The second mode of noise coupling is called inductive coupling, which means that there is some system that sets up a field. Naturally, this field has to be time varying for it to couple to your intended or your device under test, and that causes a certain EMF to be induced. So in this case, what we say is that this inductive coupling can be modeled as basically a coupled transformer, very poorly coupled transformer, where this coupling coefficient of mutual coupling is fairly low. But it doesn't really matter what these numbers are, because that's very, very highly application specific or situation specific. But this just gives a very high level sort of an electrical model for students to understand what is going on. The other two mechanisms that we talk about are what are called conducted versus radiated. So radiated basically means that noise is emitted in the form of electromagnetic waves, radiation, which travels through free space, through air, through walls, through basically all matter, and can reach the victim. Whereas conducted emission basically travels only through conductors. So only if there is a galvanic path between the source of our noise and the victim, then we have that conducted noise problem. And we look at examples of each of those. And then in the final part of this first segment, then I talk about how EMI compliance testing is actually done. Who sets the rules, who sets the standards, who decides who can test, who can certify, and so on. So, and just a little bit about the compliance and pre-compliance. So the idea is that whenever a product is ready to be sold, it needs to pass a test called the compliance test, obviously. But it's too expensive for a product designer to keep, running to the test, and let's say something fails and come back, make changes, and then go to do the test again. So most engineers would prefer to do what is called pre-compliance testing, which means you test the product for EMI compliance in-house, try to make it as close as possible to the final statutory test, and try to fix problems, find and fix problems before they actually go to the test. So the idea is to save time, money, and effort, and catch problems early in the design cycles. So again, that's just about compliance and pre-compliance, and then a few slides about how the test is actually carried out. So you would take your device to the testing house, they would place it in a very specific fashion in a very specific environment, and then they connect a spectrum analyzer or an EMI receiver, and then measure the amount of electromagnetic emission that is coming from it. So then that was for conducted. Then again, there's a test for radiated emission, which basically uses the same setup, but with an antenna. and then just a few photos to show what such a test setup or a test site would look like. So that ends the first part of this three-part series. For the second part, I will switch over to the video module, which is about 30 minutes long, and we can just watch that as it is. So if there are any questions at this point, please feel free to post them in the chat box. If you have any questions later on, you can always email me. My name is Abhijit. The email address is on the slides as well. And so let me share my let me share the video module, and we'll watch that now. So you can see that these videos are part of the Advanced Power Electronics 2 module. So you can go to the new CUSP website and then click on this Advanced Power Electronics 2 course. And then if you go to the lecture modules, then you'll see the EMI EMC segments are the last three videos here. So part one is basically what all I covered just now, just skim through it. Part two is the case studies and specific examples, which we'll go into right now. Hello everyone, and welcome to this course on electromagnetic interference and electromagnetic compatibility. This is the second video out of a set of 3 videos. My name is Abhijit, and I'll be talking in this video about some case studies. In the previous video, we have talked about an introduction to EMI, EMC, some motivation and why these concepts are important, and we have done some coverage of the background about EMI and EMC. In this video, we are going to take one circuit at a time and analyze EMI issues that may come about in each of them. The circuits are inspired by real circuits and real applications, although they are a little simplified, but they are not contrived examples, so they are fairly real world examples. So let's get started. Let's look at the first circuit here. This is a linear supply for a heater coil. I'll just give a brief background about what the circuit is and what's going on. So the application is, say, a process industry where you have a tank which contains some chemicals that need to be maintained at a fixed temperature. And to do that, we have a heater coil, which is just a resistive element, which is going to carry current and heat up and therefore keep the tank temperature at the desired value. Now, what is going to happen is that controlling the current in this heater coil is going to affect the temperature of this tank. And of course, there's going to be some feedback mechanism where there'll be a temperature sensor measuring the temperature here and feeding it back to give us the desired current that needs to be fed. Now, we've simplified this a little bit, and what we are doing here is that this is like some microcontroller or a controller which basically outputs some analog value, and that analog value is converted to the current by this op amp and this power transistor here. So now let's see what's going to happen. This heater coil is going to take a fairly large amount of current because we need to dissipate a large amount of energy, and that large current cannot be supplied by the op amp, which is why we have put a power transistor here. This heater can operate either in the linear mode, which means that the current through this heater coil can vary between 0 and the maximum, and in the extreme case it may even operate in the on-off mode, which means that when you want to heat the tank, the current may go from 0 up to the maximum value, and if you want to quickly cool the tank, the current may go from the present value back to 0. So this is the circuit. Now let's look at what's going to happen. Here we assume that the heater resistance doesn't change much as a function of the temperature, which is just a simplification we are doing. And we are assuming that this is just an open loop microcontroller based control system. So now let's see what's going to happen. First of all, we know that conductors are not ideal, which means that the wires that carry the current to the heater are going to have some amount of resistance, and they're going to have some amount of inductance or reactance. Now, what's going to happen when this large heater current flows through these wires? Here we assume that the real circuit was wired up exactly as shown in this schematic circuit diagram. Now, as I mentioned, the power lines, which means the conductors carrying this high power current, they have inductance and resistance. Now, let's look at this particular node. Based on the control variable or the amount of power that needs to be delivered, the microcontroller is going to set the voltage at this node, which is basically the non-inverting input of this op-amp. Now, based on that voltage, the op-amp is going to control the output voltage such that this node here matches the non-inverting input. Basically, the op-amp ensures that the inverting and non-inverting inputs are at the same voltage. Unfortunately, supposing we were to increase this node by a slight amount, which means we want to increase the current in the heater coil by a small amount. As a result of that, the voltage at this node will increase. When this voltage increases, this is the base voltage of this transistor, and what is going to happen is that this transistor begins to conduct better and drives a larger current down the emitter through the collector and out of the emitter. As a result, because the current through this path has increased, the voltage drop across this parasitic impedance has also increased. As a result of which, the voltage at this node is going to drop. That is because the voltage at this node is equal to the voltage here minus the drop across all these parasitic impedances. So the heavier the current we draw through this line, the more is going to be the voltage drop here. Now what is going to happen is that as the voltage to this power supply drops, basically the power pins of the op-amp effectively see a reduction in the supply voltage. Because the supply voltage goes down, the output voltage also goes down. Noise or disturbance on the power rails can cause a disturbance on the output rail. However, the important thing to note here is that because these are not purely resistive, they are partially inductive as well, these elements. There is a certain time lag between the change in current here, or rather the change in voltage, which causes a change in current, which causes a change in voltage here, and which can then feed back to cause a change in voltage here. So what we see in this loop, what has happened is that a slight change in voltage here, a slight increase here, has caused a slight decrease a little bit later. Now what happens when this voltage decreases? When this voltage decreases, the base voltage of the transistor will also decrease, and when the base voltage decreases, the current through this emitter or the collector is also going to decrease, as a result of which, when the total current drawn through the supply decreases, and this voltage will go back up. When this voltage goes back up, we see a base voltage increase again, and this cycle continues forever. This basically is a parasitic oscillator that has formed, and this can cause severe oscillation in the output depending on the circuit parameters. This is a known problem. In many audio amplifiers, under certain conditions, it could cause the output to start making a loud noise, much like a motorboat, and it used to be called motorboating. So let's see what is the solution to this. This is, of course, what we need to eliminate. We need to eliminate the effect of an increase in voltage at the input and eliminate that link through the power supply. So first thing we are going to do is eliminate the shared current path, which is what was causing the problem. So instead of wiring the op-amp supply rails to the shared node or the shared current path, we'll use separate conductors or separate wire and wire it directly to the battery. Now in this case, the high power current or the large current that was flowing through the heater flows through a different conductor, and because that current does not flow or does not have a shared conduction path with the op-amp supply rail, there is no effect of the current on the output voltage here. So that is the first solution to eliminate that problem. As you can recall, this effect is called conducted noise. Basically, change in the current here, change in current drawn by the load, was causing a change in voltage here, which was due to shared conduction path. The next thing we need to look at is the loop area. As you can see, the high current that is being drawn by the heater is taking this path shown by the dotted line here. Now we know that this current is going to be large, and it may have some switching component as well. Supposing we want to turn on or turn off the heater quickly, a large current is going to flow through this path. Now what is the area associated with this loop? That is fairly large, and if the heater coil were to turn on or turn off suddenly, we expect that a large amount of electromagnetic energy will be radiated. This can especially be a big problem if the heater coil is far away from the control system. So to reduce that problem, what we can do is reduce the area associated with this loop. Now how do we do that? We basically run the conductors as close to each other as possible. So this is an example of how that can be done. We basically use two conductors that run very close to each other, and in this case the effective area is greatly reduced. The next thing to do is that in addition to separating the power supply leads of the op-amp from the high current path, we can also add a little bit of capacitance to the power supply nodes. This is called power supply decoupling, and this basically ensures that any noise or any change in the voltage here is suppressed and does not affect the op-amp supply voltage. So we have taken 3 steps in this very simple circuit to eliminate some potential EMI and EMC problems. So to summarize, first, we have eliminated the shared current path. We have done that by wiring the heater coil directly to the power source or the battery and not allowing any of that current to flow through the leads that also carry power to the op-amp or to the control system. The second thing we did is we reduced the loop area. This reduction in loop area is done simply by running the power leads as close to each other as possible, and typically we can use cables that have multiple conductors in the same housing, or we can physically bind the conductors together depending on the application, of course. And by doing this, we reduce the area associated with this loop and therefore reduce or eliminate the amount of EM radiation or electromagnetic energy that will be radiated by this loop. The third thing that we did was to stiffen the op-amp power supply rail, which means we added a capacitance here, and this capacitance ensures that any noise in the power supply rail does not reach the op-amp supply. Next, we are going to look at a flyback converter. I assume that you are all familiar with the working of a flyback converter, and the EMI and EMC issues for this converter are going to be related to the fact that this is a switching converter and also has high dV by dt, which means the voltage at some of these nodes changes quite rapidly. In this case, we are going to take a quick look at how layout for such a converter is critical. So let's say we have some rules about the layout. We need to lay it out on a single-sided board and using only through-hole components, which means no SMD components. So here is a quick layout done by somebody who's probably not very familiar with EMI and EMC constraints. And going by the electrical circuit wise, this layout is fine, it's going to work. But let's look at what are the problems that can come about as a result of this layout. First of all, let's look at the high current path in both the circuit and correspondingly in the layout. So we see that the switching current is going to have the path as highlighted in red, and on the layout that has actually a fairly large area. And this large area can have a couple of problems. The first is that switching current is going to lead to radiated noise, which means this loop will emit EM radiation. The second thing is that these traces are non-ideal, they have impedance, and that can create ground bounce issue, which is conducted noise, which is what we saw in the previous example. So let's see what we can do to improve this layout. The first thing is we want to reduce the area, so we want to tighten up the layout a little bit. Simply by moving the components, we are able to achieve that, and you can see that I've changed the layout a little bit now using the same components, the same footprints, but just changing their positioning in order to virtually eliminate the high current loop area. And it is important to note in this case that not only is the primary side important, but the secondary side as well, because both sides are going to have switching currents. Just a side note here is that most of the switching current will come through this capacitance, and what we saw in the previous example was that the capacitance has to have a very low impedance for these high frequency currents. So typically designers will select a capacitance with very low equivalent series impedance, that is the ESR and ESL in such applications. Now let's look at what's going to happen to the op-amp in our circuit, which is just representative of other circuits that may be next to the switching power supply. So earlier we saw that the current was flowing through this conducted, through this trace, and like in the previous example, this is going to cause a ground bounce at this node, which means that the power supply for this op-amp is going to change and can result in noise coming at the output. In the improved circuit, in the improved layout, what we've done is we've eliminated the shared current path, and the op-amp supply now does not share any trace with the high current path. So we eliminate that problem as well, and that eliminates ground noise or conducted noise from reaching the op-amp. Now let's look at what is called differential mode noise. Consider the flyback switching part of the flyback converter. Let's say it's connected to a DC source which is slightly far away. It could be a battery or it could be just a wall mounted power supply. And the current that is drawn by this flyback converter has a triangular shape, as we know. So it's going to draw this triangular shaped current when the switch is on, and this dotted line shows the current that freewheels through the secondary when this main FET turns off. So we are concerned more with the primary side current to begin with. Now most of this current, as we know, is going to come from this capacitance, and as we also know, this capacitance has some impedance which is called the equivalent series impedance. This is the ESR and the ESL, equivalent series resistance, equivalent series impedance or inductance. And the lines that connect this power supply VCC are also not ideal, so they are going to have some impedance as well. Based on the two impedances, most of the current is going to come from this capacitor, because we expect that this impedance is going to be really low, but some current can still come directly from the power supply. Of course, we are talking about high frequency currents here. If there was some other system also connected across these nodes here, then the voltage seen by this piece of equipment is going to be the VCC minus the drop across the series impedance. And the drop across this series impedance is dependent on how much current is drawn by this. So in this case, the ratio of impedances, these two, is going to determine how much noise is seen by this victim. Now let's look at some issues with the heat sink. Now we know that in a sizable power electronic converter, the switch dissipates a fair amount of energy. So what's going to happen to the VDS at this drain node? So that's fairly simple. We know that when the switch is on, VDS is 0. When the switch turns off, the inductance freewheels through the secondary side like this, and the output voltage is VCC plus VO. And depending on whether or not we are in DCM, we may also have a third state here, which is VCC. And each of these transitions is going to be going to have a very high dV by dt. And depending on how fast we are switching this, what device it is, that will determine how fast these edges are. And so basically VDS is going to be trapezoidal, and the fundamental frequency is going to be the same as the switching frequency of this converter. And all of these are high dV by dt transitions. So now let's look at how this VDS is going to cause EMI problems. We know that this FET or power semiconductor switch is going to need a heat sink, and in most semiconductor switches, the drain of the MOSFET, or the collector in case of BJTs, is connected to the heatsink tab to be able to dissipate heat in the most effective way. If we don't do anything and we just leave this transistor freestanding, then this is going to act like a stub antenna, which we discussed earlier, and whichever higher harmonic matches the stub wavelength, that frequency will radiate, and basically we may fail the radiated emission test. Supposing we add a large heat sink, that heat sink just becomes a bigger antenna, and sometimes the fins on the heat sink can improve or change the directionality of that antenna as well. So that's not such a good idea. As I mentioned, the tab case or heat sink often has a large area by design because it has to dissipate a lot of energy and forms one parallel plate of a capacitance. Because this voltage is switching, this large area can couple noise into other parts of the circuit as well. So this is the second problem with VDS having a switching voltage. So we can have noise induced in other nearby parts of the circuit just by having switching voltage at the drain. Now, one solution is to simply ground the heatsink, but often it can't be done. One of the reasons is that the heatsink can't have high voltages, so we can't have it exposed. And many times the heatsink is connected to multiple devices, and as a result, we cannot ground the heatsink directly. And in some cases, the equipment body acts as the heatsink. So we need some electrical insulation between the case and the heatsink. So what do we do? Typically, we add some mica, and what is going to happen as a result is that it's going to form a parasitic capacitance between the actual heatsink and the power device. Now, if we leave this heatsink floating, we can still get some amount of coupling based on the parasitic capacitance here and the parasitic capacitance here. There's still going to be some noise that couples into our nearby circuits. So to analyze this situation, what we can do is we can model this entire system as a switching noise voltage connected to the drain, and how that affects the system. So we saw that we can't leave this floating, so where can we connect? One way is we can connect it directly to the return. Now basically this is the ideal solution, and it shorts out this parasitic capacitance that is formed, and now no more energy will couple into the victim. So we've solved the problem. However, this is not possible if this heatsink is exposed and has to be grounded, or it is connected to the chassis of the system, and so on. What happens if we were to ground this heatsink? Which means we connect this heatsink to the earth of the equipment. Now, what does the circuit look like for the high frequency voltage at this drain? So let's do the modeling, and this is what it looks like. This inductor is basically an open or high impedance for high frequency. This capacitor is effectively a short, and these line and neutral lines are connected to the VCC and ground through a rectifier, and at any time 2 of these diodes are always conducting. So let's just look at an instance where these 2 diodes are conducting. So the high frequency current is going to have this path that is highlighted in the circuit diagram. Basically it flows all the way out, and wherever there is coupling, capacitive coupling between the live and neutral wires and the earth, the current will circulate like this. In fact, this earth is often tied directly to the neutral at the far end, so the current can flow all the way out and then come back. Now what's the problem here? The problem is that this large loop can set up EM fields, and this can radiate, and the other thing is that current flowing through this line constitutes conducted emission, which is not allowed and which is limited by the EMI standards. So we need to reduce that. Now let's just quickly contrast common mode and differential mode paths. So we saw that this current can take one of 2 paths. It can flow either through either the live wire or the neutral wire, and this is why it is called common mode current, because it is common to both lines. In contrast, the differential mode current that we saw in the previous analysis of the flyback converter flows in through the line and then back through the neutral. So again, just to recap, what is the problem with common mode? One is that we will fail radiated and conducted noise limits, and we'll fail compliance testing. So what is the solution for common mode noise? If you were to add the filter like we did earlier, this is not going to solve the problem entirely, because common mode noise can bypass or has a bypass path through the other power line. So this is not going to help much. Inductance on one power line does not affect common mode noise. So what we can do is we can add this inductance in a split form. We can add it to both of the power lines, and this should affect common mode as well as differential mode noise. The net impedance seen by the common mode is the parallel combination of impedance on these 2 lines. Now what if we want to eliminate common mode current altogether? You see, typically we have some constraints. One of them is that the heatsink must be grounded. We don't want any current through the ground line, and we also want to eliminate radiated and conducted noise. So in this case, the easiest solution to that is to add a copper shield between the case and the heatsink. And this copper shield is just a thin layer of conducting material, usually copper, and that is placed between the case of the semiconductor device or the heatsink tab and the actual heatsink, and the heatsink can be grounded. Now let's look at the equivalent circuit model for this. We have now formed 2 parasitic capacitances. The noise source, which was the VDS switching voltage, is now shorted out by this shield strap or the shield foil, and we have eliminated the problem of switching noise. This is an example of how this might be implemented. We have the transistor here, we have an insulating material which is a sill pad, and we have a copper shield which is connected to the negative terminal, and we have a grounded heatsink which is connected. So all these are thermally conductive, but only the copper is an electrical conductor. A similar situation is seen due to inter and intra-winding capacitances in the flyback transformer. Since the primary and secondary windings are in close proximity, a large capacitance can develop between these 2 windings. This is a parasitic capacitance. This parasitic capacitance can be modeled as 2 physical bulk capacitors, and they are shown in the figure below. Remember that these are actually distributed capacitance, but for the purpose of our analysis and modeling, we are going to model them as 2 bulk capacitances. Let us add this parasitic capacitance and see how that is going to affect the EMI and EMC issues in the circuit. In particular, we are going to see how it gives rise to common mode issues. First, we add the parasitic interwinding capacitances and the noise source that we have, as we have already discussed. Now we will identify the current path. The inductor is a high frequency, has high impedance at high frequency, and therefore is an open circuit. The parasitic capacitors have low impedance and therefore are a short at high frequency. Now note that there is some capacitance between the output negative rail and the input negative rail. This may be due to proximity or coupling through the chassis, etc. Now it can be seen that the high frequency current will now flow through the negative rail of the output and pollute the output rails. So basically this current is going to flow out through these two capacitances and appear here. Any impedance on these traces will give rise to a noise voltage at this node. In some applications, as I mentioned earlier, the output terminal must also be grounded. Now let's see what will happen in case the output terminal needs to be grounded on this side. As before, we first draw the circuit diagram. We substitute and add in the parasitic components, in this case the noise voltage, the interwinding capacitances, which we have modeled as bulk capacitances as I mentioned earlier, and parasitic capacitances between the line and neutral wires and the earth conductor. Now we know that the inductor is an open at high frequency, which is what is shown here, and the capacitances are near shorts, and you can see that this large capacitance will present a near short at high frequency. Now let's trace the high frequency current path, which will show us common mode currents. So you can see that this high frequency current from this noise source is going to flow equally through both these parasitic capacitances and is going to flow out through the line and back into back to the source. So we can see that this is going to give rise to common mode issues. So what is the solution to eliminate this common mode problem? Can we take inspiration from the solution that we used for the heatsink? The answer is yes, we can. We need to add a shield conductor or a strap between the two windings as shown here. This will work in the same way as the heatsink shield, but we have to be a little careful in this case because the shield must not form a complete turn. If it forms a complete turn, then it will form a shorted winding and we'll end up shorting the transformer or the flyback inductor, and we don't want this. So we have to be careful that the shield does not form a complete turn. The equivalent circuit is now shown here below, and we can see that what has happened is that the parasitic capacitance between the primary and secondary windings has now been split by adding this conductor in the middle. Now the question is, where should we connect this shield in order to eliminate the common mode problem? So let's see that. Now we need to connect this shield to the non-switching end of the primary winding, and I'll explain why. We should basically connect this to the source of the FET because that's how we can short out the noise source. But if you want to connect this directly to the source terminal of the FET, it may require a large or a long wire, and that may just cause more radiated emission. Instead of that, we know that at high frequency, one of the terminals, that is this terminal, is shorted to the ground anyway. That's because the bulk capacitance, the DC capacitance, is a short at high frequency, and so we can use a relatively short piece of wire and connect the shield conductor to this terminal here. As an exercise, you should think about what will happen if we connect the shield to the other terminal. So if we take the shield and connect it here, which is the drain of the MOSFET. Now, if we connect the secondary side of the high frequency transformer to some switching circuit, then it is possible that the secondary side will have some noise voltage as well, and the shield can cause some of that noise to come from the secondary back to the primary. So what is the solution in such a case? We add two shields, and one of them will be connected to the non-switching end of the primary, and the other one will be connected to the non-switching end of the secondary side. This brings us to the end of this section. Just to recap, we saw a number of real circuits. We looked at the EMI issues in each of those and the solutions for each problem. You should now be able to look at any circuit and able to anticipate and address the EMI issues that may come about. And the next video is the third and last video in the series and contains some example problems and solutions to the same. Thank you for sticking with me. So it's been about 30-35 minutes of case studies. We looked at a number of different circuits. I hope I was able to convey the basic ideas in EMI and EMC for power electronics through these examples. The reason that I picked examples instead of doing concepts is that for students especially it becomes very dry to just look at completely abstract theoretical just theoretical content, and so I thought that this would be a better way to address these topics. So the final sort of part in this is that there are a few problems. But I'm sure it's been a long day and you don't want to see the whole video, which of course is there on CUSP. You can see it in basically module 14. That's the last video module that is available in Advanced Power Electronics 2. But I will now show you the two homework assignments that have a lot of numerical problems, and I'll just really quickly skim through the various concepts that would be tested by these questions, and those should sort of help you design your own problems, design your own exam problems, or create new problems that you want your students to be able to solve. And ideally, the best thing you could do as instructors would be to combine these topics or these concepts with other things that you've already covered. So if you have covered converters, then you could talk about converters in context of EMI. If you have already talked about some sort of analog circuits or anything else, then you could weave that into your treatment of EMI and EMC as well. So now I'm going to go to the homework problems that I had given out. There we are. So these are some of the example problems. So in general, of course, for the assignment, we wanted to keep it very close to what was already covered in class, and so we just took the same heater example from the first example, and we modified it a little bit. This is not really an EMI EMC type issue in the strictest sense, but half of EMI and EMC, I believe, is to be able to figure out what's going on in a real circuit by modeling it correctly and being able to identify what's going on. And so this first problem is sort of an exercise in that. So here the idea is if the resistance of the cables changes, let's say they age or get degraded, whatever, how should you redesign the circuit to take that into account? So of course, one of the solutions is to make it a current source type system. The other is to take feedback using like a 4-wire measurement and feedback. And of course, in my experience, I found that students came up with lots of creative ways in which they could do this. So that's the first problem. The second one is a system where so second one is this circuit like this, where you have a mobile say sensing mode, it's called, powered by a DC source. It has some sensors, it has some signal conditioning, and it has a microcontroller to sense, convert all that information to digital, and then a radio transmitter to send that out. So it's a simple IoT device. And the question here is, you know, based on some known parameters of how this Wi-Fi module draws peaking currents, high di by dt, what do you do to make sure that that does not affect the sensing? So this would be an example of students wanting to look at conducted emissions. And depending on how well versed your students are with analog, with things like common mode noise rejection, or like that is basically CMRR, or things like that in op amps and analog, then you might want to weave that in as well. So again, the solution for this, I solved this entire problem in the module, the last video module, that is module 14. So feel free to go take a look at that. Then the last thing that I did, which was a circuit that they hadn't seen, but I explained the circuit in class, was a classic boost PFC converter. So we saw this circuit in a slightly different form, of course, but we saw that in the material that Professor Mohan covered. And we've already talked about why it's important to have power factor correction, why it's important to have unity power factor circuits, why it's important to draw power at unity power factor, or at least at a controlled power factor. So based on all that discussion that's already been touched on, we can use this boost PFC as another example of EMI issues in a real power electronic circuit. And this question is designed to be more open-ended. So instead of pointing out problems and asking them to solve it, I asked students to identify and label what the problems could be, and then how would they go about solving it. So of course, the first few problems are fairly straightforward. So there will be differential mode noise being drawn. There would be a VDS or VCE problem due to this node switching here. There could be an issue with loop areas. You know, you want to keep this loop area minimum, you want to keep this loop area minimum, and so on. So again, this problem is also solved in the video module. So those are the three problems that were given as homework or exercise problems. And then we have another set of problems that are available to instructors. If those of you who are members of CUSP can go and see the problems, they can see the solutions as well. And then because they're because they're limited, you can use them as problems for your exams or any other assignments as well. So that sort of brings me to the end of the material that I wanted to cover. If there are any questions, I'd be happy to take them now, or if you would prefer to email them in, that's fine as well. We'll try to answer them as soon as we can, but at least early next week. The other thing is the video material from this entire course. Of course, all of the videos that we have shown you are all available on CUSP already. We have just migrated from the old website to the new website. If you notice any hiccups, if you find something amiss, please feel free to reach out to us. We have also added a lot of new material, so hopefully your experience should be much better. So if you have any questions finally for the last few minutes, feel free to put them in the chat box. Otherwise, thank you again on behalf of Professor Mohan, Professor Robbins, Jairam, me, and Siddharth. Thank you for attending, and have a good evening, have a good weekend. So we'll close here, and thanks again. Goodbye.